Beneath the silent glow of Earth's night sky, a question has lingered longer than language itself. It rises from the quiet breath of civilizations long vanished, etched into stone, whispered in temples, woven into stories whose authors no longer have names. The same thought, the same tremor, passing through generations. Somewhere beyond this fragile world, does another mind wait to be found? Earth drifts through a cosmic ocean so vast that no human metaphor survives its measurement. Around it lies a darkness not empty, but crowded, trillions of stars, burning like distant embers. Thousands of galaxies beyond sight, each carrying more suns than humanity could count. Yet the silence is absolute. For all the brilliance scattered across the heavens, not a single voice reaches back. The paradox becomes a wound in human knowledge. If life blooms from matter, shaped by physics and time, then probability alone suggests that consciousness should have risen countless times before. The universe is ancient, older than the story of Earth by billions of years. Stars have lived and died long before our sun formed. Worlds have cooled, oceans have filled, atmospheres have thickened, perhaps turning to rain and life and memory. And yet the sky remains mute. In that silence, humanity finds its own reflection. The search for other minds becomes a search for meaning, an inquiry into the architecture of existence. Whether another civilization waits in the dark or whether Earth carries the only voice ever born, the question reveals itself. Discovering others is discovering ourselves, understanding why life emerged, where it is going, and whether the universe intends for consciousness to be rare or infinitely repeated. When the question first began, dawn of cosmic curiosity. Long before spacefaring machines broke the sky, long before mathematics became language, humanity stood beneath a darkened vault and wondered. In the absence of science, the stars became myth. They hung in the black like burning seeds, scattered with intentional precision, forming maps of gods, hunters, serpents, and forgotten kingdoms. The earliest civilizations carried no telescopes, but they held imagination, and imagination became astronomy's first instrument. Ancient Babylon watched the heavens carefully, carving celestial records into clay tablets. They charted wandering lights, planets, tracing their motions through the constellations. Egypt aligned pyramids with stellar axes. The Maya timed agricultural cycles by the drift of constellations across seasons, seeing order in the slow turning of the sky. These early observers did not ask whether life existed beyond Earth. The very structure of their world seemed bound tightly to the heavens themselves. Stars were protectors, judges, or symbols of destiny, not distant suns. Yet curiosity grows where uncertainty breathes. Somewhere between ritual and silence, the first scientific question emerged. Greek philosophers stepped away from divine explanation, not with instruments, but with thought alone. Among them was Democritus, a thinker who envisioned the universe as infinite, boundless, uncentered, filled with innumerable worlds. He suggested that nature does not craft a single instance of anything. If matter forms one world, it forms countless others. Though no telescope existed to verify his vision, his idea planted something irreversible: the possibility that Earth was not the first and not the only. Humanity's imagination could conceive plurality even without evidence. Time advanced, and the night sky remained unchanged, but human reasoning deepened. Aristotle described the cosmos as complete, enclosed, perfect. Earth was its center, with celestial spheres turning around it. In this model, life elsewhere became unnecessary, even impossible. For many centuries, this Earth-centered geometry remained unchallenged. The notion of other worlds drifted back into mystery. Then the sky shifted, not physically but philosophically. Nicholas Copernicus, studying planetary motion, noticed something profound. The strange backward curves of Mars and the wandering instability of Jupiter made sense only if Earth was not stationary. His model placed Earth as a planet in orbit around the Sun. It was not the center of existence, merely one world among others. This realization moved slowly through Europe, resisted by tradition. Yet the seed had germinated. If Earth was only a world, then worlds could be many. A century later, Galileo Galilei turned a crafted tube of glass toward the moon. Through magnification, the lunar surface revealed mountains and craters, scars of geological history. These were not divine circles etched by perfection, but landforms shaped by violence and time, not unlike Earth's own. He aimed the same lens toward Jupiter and found 4 moons circling the gas giant, individual, persistent worlds with orbits of their own. In that moment, the universe expanded. Not physically, for the stars had always existed. Mentally, for humanity now understood that Earth shared the heavens with other landscapes. If moons could be worlds, worlds could be places. And if they were places, the possibility of life could no longer be confined to Earth alone. Johannes Kepler added another layer of wonder. Where others calculated orbits, Kepler imagined what such worlds might hold. He wrote of lunar inhabitants as philosophical speculation, not fiction, proposing that nature may breathe differently across different environments. He never claimed life existed elsewhere, he only argued that nothing forbade it. That subtle distinction transformed an ancient dream into a scientific hypothesis. It was no longer divine speculation, it was testable possibility. Across the next centuries, telescopes sharpened. Uranus emerged, then Neptune, then faint objects drifting beyond. Discovery after discovery fractured old certainty. If Earth had once seemed solitary, now it resembled merely one element in a structure far larger than imagination had been able to construct. But the emotional turn did not occur because the heavens grew larger. It occurred because Earth grew smaller. Every new discovery acted like a mirror, reducing humanity's specialness, replacing sentimental singularity with rational plurality. The night sky was no longer a ceiling, it was a map without borders. The philosophical consequences were immense. If the cosmos contained countless worlds, might it also contain countless beginnings of life? More importantly, might it contain countless endings? Civilizations rising, fading, forgotten, their light extinguished long before human existence began? When telescopes expanded into observatories, the question multiplied. The stars were no longer unreachable conceptually, they became measurable structures. Their colors revealed temperatures, their motion revealed gravitational relationships. Life ceased being mythic. It became a variable in cosmological calculation. Some historians argue that the moment humanity stopped believing in uniqueness was the moment science began searching for intelligence. Scientific humility opened a doorway into the unknown. Still, the mystery carried weight. If there were other civilizations, where had their voices gone? If countless suns existed, why was the cosmic sea silent? These questions would not be answered in ancient observatories, but the dawn had begun. Curiosity was awake. Yet behind every discovery was an emotional thread woven quietly across centuries. It was not simply that Earth was ordinary, it was that Earth might be temporary. To imagine other worlds was to imagine that intelligence was not a one-time event, not confined to one epoch, not stationed in one evolutionary path. Such a realization carried both hope and unease. Hope that humanity might someday find kinship written across light years. Unease that other civilizations might already have existed and vanished, leaving no trace except cosmic quietness. The ancient astronomers, without knowing it, began a story that science would later inherit. They carved star maps in stone, not realizing that those same stars were suns. They traced patterns across constellations, unaware that those patterns hinted at infinity. They measured cycles for planting and harvest, never knowing that each cycle corresponded to the tilt of a planet revolving through cosmic space. Science now interprets what ancient eyes only witnessed. And yet, the emotional truth remains unchanged. When humanity first understood that Earth was not central, the universe ceased being moral theater and became a physical landscape. Across that landscape, life could exist, evolve, awaken, disappear, and never be known. The dawn of cosmic curiosity began not with technology, but with humility, an awareness that the sky did not revolve around Earth, and therefore existence might not revolve around humanity. Every new world discovered since has been an echo of that realization. And behind it lies the question that refuses to fade. Not whether other life exists, but whether humanity will ever prove that it does, or whether the stars have witnessed countless civilizations already, their memories swallowed by time, their signals gone silent, leaving the question suspended across the darkness. If Earth is not unique, then what else once lived, and what waits to be found? The first real clue, when Mars became a question. In the closing decades of the 19th century, the red planet drifted across the sky like a faint ember, close enough to imagine yet forever out of reach. Through modest telescopes, it appeared as a tawny disk, dusted with irregular dark patches and crowned by shifting pale caps. Mars was unlike any other point of light that wandered the heavens. It had surface tones, seasons, and subtle changes. These patterns whispered possibility. In 1877, during a particularly favorable alignment, Giovanni Schiaparelli directed his telescope toward that copper-colored world and noted delicate linear features running across the surface. He called them canali, channels, an innocent word in Italian, but a word destined for misinterpretation. To the scientific public beyond Italy, canali became translated as canals, a term that implied deliberate construction, engineering, purpose. Mars was suddenly not a barren sphere of dust. It was imagined as landscaped. The idea did not fade quietly. It expanded. The late 19th century was a time of optimism about civilization, industry, and engineering. Human empires carved waterways across continents. Cities tamed rivers and redirected them. Irrigation brought deserts to life. The notion that an advanced civilization might reshape a planet resonated with cultural momentum. Percival Lowell, an aristocratic thinker of extraordinary conviction, looked at Schiaparelli's descriptions and believed them literal. From an observatory he built in Arizona, he sketched sweeping straight lines crossing Mars like highways of intention. He proposed that an intelligent society lived beneath thinning Martian skies, drawing water from receding polar ice, transporting it across deserts, and sustaining life on the edge of extinction. Lowell published maps. He wrote books. He lectured. And with each claim, Mars expanded in the human mind. People imagined cities bordering winding canals, orchards nourished by polar meltwater, deserts transformed into agriculture. Fiction grew around the speculation, echoing through literature, theater, and early radio. Mars became the first world in human history seriously considered as inhabited, not mythically, but scientifically. Not everyone agreed. Observers using similar telescopes reported no sharply defined lines. Some saw faint streaks, some nothing at all. Critics suggested that Lowell's symmetrical lines reflected not planetary geography but the structure of the human eye, neurons filling gaps between indistinct observations. Yet the debate was not enough to dissolve the vision of an engineered planet. The idea was intoxicating. Mars became humanity's mirror, a nearby consciousness waiting to be discovered. As telescopes sharpened, the irregular markings softened. The lines blurred. Some vanished entirely. Others changed positions depending on the day. The scientific community grew skeptical, yet the hope remained intact because Mars still behaved like a world with memory. It had storms that rolled like continents of dust. It bore caps of frost that receded in summer and thickened in winter. It changed color in seasons, as though landscapes were awakening and fading. The early 20th century nurtured the last great wave of optimistic Martian speculation. Then a new era of technology dissolved the illusion. When spacecraft first departed Earth in the 1960s, their destinations were aimed squarely at Mars. Mariner 4 swept past the planet in 1965, transmitting the first close images ever received from another world. Each image took hours to decode. When assembled, they revealed not a civilization but a desolate expanse, cratered, ancient, battered by time. The surface resembled the moon far more than Earth. No geometrically perfect lines. No networks of engineered waterways. Only silence. Mariner 9 arrived later and orbited the planet, unveiling landscapes sculpted not by intelligence but by geology. Enormous extinct volcanoes rose higher than any found on Earth. A canyon system, the depth of mountain ranges and the length of continents, opened across the equatorial region. Ancient dried channels existed, carved not by societies but by vanished rivers. The revelation hurt, though science does not often describe disappointment. The dream dissolved into dust. And yet, something in that disappointment strengthened the original mystery. Because if Mars was barren now, what had it once been? The sediment patterns implied long flows of liquid. The layered rock formations suggested standing water, a stable ocean or vast lakes. Valley networks branched like terrestrial river systems. Gullies appeared where liquid had once eroded stone. The polar caps contained frozen reserves, not minerals, but pure water ice. Early telescopic error transformed into accurate forensic insight. The question did not die. It evolved. Lowell's canals vanished, but evidence formed of a different kind. Mars once had atmosphere thick enough to support weather, clouds, rain. It bore magnetic scars implying an ancient planetary dynamo that had stopped spinning. Something had drained its air, stripped its water, and left behind a quiet skeleton. Hope turned into scientific pursuit. The Viking landers arrived in the 1970s, touching Martian soil gently, like archaeologists arriving late. They tested the dirt for metabolism, chemistry, biological residue. The results were ambiguous. Chemical reactions mimicked life, though no cells emerged. In ambiguity, imagination persisted. The emotional arc deepened. Humanity had imagined neighbors across a narrow void, only to find silence. The silence, paradoxically, expanded the mystery. If Mars once held oceans, could it also have held biology? Had evolution begun and then receded? Had an entire planetary experiment faded beneath cosmic cold? The disappointment no longer represented failure. It represented possibility. Mars became humanity's first lesson in planetary fragility. It proved that worlds do not remain stable, that climates dissolve, atmospheres thin, magnetospheres vanish, oceans retreat into frozen shadows. If life once tried to bloom there, then Mars taught that life may not endure everywhere it begins. Scientifically, Mars became evidence of cosmic impermanence. But culturally, Mars became evidence of longing, that somewhere life must exist, and the nearest test subject simply arrived too late. The longing survived because what the spacecraft found was not emptiness. It was incomplete history. Fossil water channels, ancient deltas, mineral signatures legible only through chemistry. Mars no longer offered civilization. It offered biography. And through biography, a deeper question emerged. If life found a foothold there for even a geological moment, did it ever leave residue, microbial fossils, preserved cells, dormant organics waiting beneath ice? Later missions sharpened the question. Mars rovers rolled slowly over plains once thought meaningless and uncovered clay minerals, carbon-based compounds, sulfur cycles. Cameras showed horizon lines softened by atmospheric haze. Dust devils swirled across dunes. Radiation crackled against unprotected soil. Mars was not dead. It was recovering. And so, the first great cosmic disappointment became the first scientifically reasoned hope. Life might not thrive there now, but life once had conditions under which it could have formed. Mars shifted from imagined civilization to evidence of planetary mortality. From canals to crater basins. From cities to sediments. Yet even when stripped of its fantastical stories, Mars continued to point outward. If one world near Earth once carried the building blocks of biology, then statistically, the night sky no longer represented a silence of impossibility. Instead, it represented a silence awaiting interpretation. The failure to find intelligence did not close the question. It opened the method. Martian dust taught humanity what to search for elsewhere. Methane signatures, mineralogical traces, isotopic ratios, biosignature gases. And deeper still, it taught that life might disappear long before intelligence rises, raising the haunting possibility that civilizations may not survive long enough to speak. Mars was never proof of alien life. Mars was proof that worlds change. And through that change, the idea of cosmic companionship shifted from speculation to research. Hope met scientific reality. Yet the desire survived. The shocking paradox, Enrico Fermi and Why the Sky is Silent. At a cafeteria table in the high desert of New Mexico, beneath the shadow of mountains scorched by atomic flame, four physicists paused over their lunch. The year was 1950, and Los Alamos National Laboratory was still steeped in secrecy, an institution built around equations that reshaped the nature of war. The conversation wandered casually, drifting among scientific gossip, new calculations, and the future of technology. And then, almost without ceremony, one question landed like a quiet detonation. "Where is everybody?" The remark belonged to Enrico Fermi, one of the architects of the nuclear age. The tone was not humorous, nor poetic, just simple, almost childlike. But simplicity has a strange power in science. In that cafeteria, his colleagues laughed, then hesitated, because the question did not fade. It deepened. It expanded. And suddenly, the silence of the universe felt loud. The question emerged from numbers, cold, indifferent, undeniable. By the mid-20th century, astronomers already knew that the Milky Way was old. Nearly 13.6 billion years had passed since its first stars ignited. The Sun, by contrast, was a young flame, barely 4.6 billion years into its life. That meant the majority of stars above Earth's atmosphere had existed long before the solar system ever formed. Some stars had burned, bloomed, and died before Earth cooled into oceans. Some had planets ancient enough to have birthed civilizations before Earth's continents even settled. Mathematically, life should not merely be possible, it should be prolific. A galaxy of roughly 400 billion suns, with an estimated tens of billions of Earth-like worlds. Worlds with water, carbon, sunlight, geological cycles, atmospheres capable of chemistry. Researchers such as Frank Drake and later Michael Hart would argue that with such numerical abundance, probability alone should have forced intelligent life to arise repeatedly. And if intelligence could arise, then so should engineering. Time became the decisive force. Suppose a civilization invented radio 1,000,000 years ago, or 1,000,000 years before that, or 200 million. From that vantage point, humanity is not advanced. Humanity is a late arrival, barely formed, still confused, still wandering. So Fermi asked his question again. If civilizations could have emerged millions of years ago, why does the night sky remain silent? Human reasoning pushes toward a simple logic. Technological life should spread. Maybe not colonization in the earthly sense. No fleets, no conquest, no empire, but diffusion. A species able to manipulate energy should, eventually, manipulate distances. Even at slow speeds, even with patient drift across starfields, 1,000,000 years is more than enough. 1,000,000 years is enough to spread across clusters, enough to build signal networks, enough to leave trails, artifacts, spectra, megastructures, chemical scars in planetary atmospheres. But the telescopes find none. Radio arrays listen, and the receivers remain empty. The cosmic microwave background whispers its primordial song, but no modulation crosses its ancient static. Deep sky surveys measure starlight curves, searching for shadows of Dyson shells, vast structures that would encase stars in a shell of energy-harvesting architecture. But nothing reveals itself. The universe glows, but it glows naturally. So again, if intelligence exists beyond Earth, why has it left no mark? That was Fermi's paradox. Not a mystery from philosophy, not a fable or a speculation, but a contradiction written between two very real facts. The galaxy is ancient enough for civilizations to have arisen long before humans. No trace of such civilizations is observed. It was as though the universe had erased its own witnesses. In scientific history, a single idea sometimes cleaves the world into before and after. The structure of DNA, quantum mechanics, relativity. The Fermi paradox belongs to this category, not because of equations, but because of implication. Fermi's moment changed how humanity interprets itself. Before that question, Earth felt like an ordinary place within a crowded universe. After it, Earth seemed isolated, occasionally profound, occasionally frightening. The argument did not stay confined to lunch conversation. Physicists and astronomers began probing it mathematically. Frank Tipler later estimated that even at extremely slow expansion speeds, a technological civilization could traverse or emulate every star in the galaxy within roughly 100 million years, less than 1% of the Milky Way's age. Michael Hart extended the reasoning. If expansion was possible, then the absence of expansion implied a deeper truth. Maybe no civilization had ever existed long enough to reach outward. Maybe intelligence extinguishes itself. Maybe technological maturity is unstable. Or maybe the cosmos enforces silence. The paradox shook more than astronomy. It struck at identity. For thousands of years, civilizations imagined themselves surrounded by gods, by spirits, by celestial neighbors. Even early science assumed abundance. Mars was once imagined as irrigated farmland. Venus was thought to be humid jungle. The nearest stars were assumed to be dotted with life. But now observation overturned imagination. The Mariner missions found no canals on Mars. The Venera probes found no forests on Venus. No moons yielded ruins. No atmospheres revealed engineered gases. In place of company came emptiness. The universe, once warm with possibility, became cold. Yet silence is not absence, only unanswered potential. So researchers tried to explain it. Perhaps civilizations do not desire expansion. Perhaps intelligence turns inward, into computation, into digital ecologies, into internal universes built of mathematics rather than matter. Perhaps civilizations perish from self-eradication or climatic collapse, or transformation into forms unseen, biological, artificial, quantum-based. Or perhaps life exists, but communication is impossible. Distances swallow intention. Velocities limit contact. Signal decay dissolves meaning into static. The paradox remained, but speculation multiplied. And beneath all of it lies one uncomfortable symmetry. Humanity listens, but it also transmits. Earth leaks radio into space, faint, scattered, unintentional. Every broadcast, every navigation ping, every scientific transmission, slowly diffusing outward. The earliest signals now expand beyond 100 light-years. If other civilizations behave as humans do, then traces should exist. And yet they do not. Humans assume their noise is meaningful, detectable. But space dilutes it until it dissolves into the cosmic background. Perhaps the cosmos is full of civilizations transmitting into the dark. But every signal fades before reaching another. Between stars, silence is not a condition, it is geometry. And geometry wins. Still, science cannot abandon the question. Because the paradox is not merely academic, it defines humanity's location in time. If the universe is silent because life is rare, then Earth is not simply planetary, it is statistically profound. If silence exists because intelligence dies quickly, then humanity stands within a narrow window, a temporary moment between awakening and disappearance. And if silence is illusion, masking civilizations beyond detection, then humanity is still primitive, like early creatures learning to generate sound without understanding how far sound can travel. In 1950, Fermi placed humanity between these possibilities. Not comfortably, not confidently, but honestly. And beneath his question lies a deeper implication, one that cannot be measured by telescopes or equations. If everywhere is empty, then everything here is extraordinary. Every cell, every language, every idea. Against cosmic probability, meaning has emerged. The paradox did not fade with time. Modern exoplanet surveys deepened it. NASA's Kepler mission revealed thousands of worlds, many Earth-sized, some within star-habitable zones. Later statistical inference estimated potentially tens of billions of Earth-like planets in the galaxy. Probability moved from speculation to dataset. Then came the James Webb Space Telescope, detecting carbon dioxide on distant worlds, methane in alien atmospheres, signatures of oxygen cycles, temperature gradients, planetary oceans covered by cloud veils. But still, no industrial traces. No unusual energy signatures. No structured light. No engineered atmospheric chemicals. The paradox hardened. It sharpened. The universe grew larger, but its silence grew louder. And yet, human imagination does not collapse. Because silence is not an answer. Silence is an invitation. Fermi's lunch question remains suspended, the same way early questions once hung over continents uncharted, oceans unmapped, skies unexplored. The paradox does not diminish the search, it anchors it. In the quiet between stars, a possibility continues. Perhaps the first voice to break the silence has not spoken yet. Perhaps the universe waits not to reveal itself, but to be revealed. And perhaps the moment Fermi articulated, the moment when numbers confronted emptiness, was not a moment of cosmic loneliness, but a beginning. A doorway into the unknown. A reminder that mystery is not absence. It is the shape of discovery waiting to form. In the silence, the question survives. Where is everybody? And somewhere, beyond measurable distance, the answer waits. Data from the stars, SETI, radios, and listening to the dark. The modern search for voices beyond Earth began not with rockets, nor telescopes, but with an idea. If intelligence exists elsewhere, it may reveal itself not through presence, but through patterns. From that premise arose SETI, the search for extraterrestrial intelligence. Its origins were fragile, almost hypothetical. In the late 1950s, scientists began to realize something remarkable. Radio waves could cross interstellar space with minimal distortion. Unlike light visible to the eye, radio could slip through dust, glide past interstellar clouds, and travel for thousands of years unbroken. The universe, once assumed visually silent, became a possible broadcast field. And so humanity built instruments designed not to look outward but to listen. The movement found one of its most powerful advocates in Carl Sagan. He imagined civilizations separated by distances so vast that travel was irrelevant, but communication remained possible. A message, encoded, intentional, could leap centuries of darkness and still arrive. Sagan's reasoning held a poetic clarity. If intelligence wants to be known, it will use physics. Hydrogen, the most abundant element in the universe, emits a radio signature at 1,420 MHz. Any civilization studying astronomy would know this frequency. Any civilization transmitting deliberately might anchor messages near it. That frequency became sacred ground for listening. From scattered observatories emerged a purpose: detect evidence of thought. Not life, not biology, thought. Because thinking is measurable. In Puerto Rico, a vast metal bowl was sculpted into the hills, Arecibo Observatory. At the time of its completion, it was the largest single-dish radio telescope on Earth. It behaved like an ear pressed against the void, open to frequencies no biological ear could ever receive. Its structure did not move, the sky moved above it. Day by day, star systems slid across its focus. Arecibo waited. For decades, the observatory pulled down data streams, unbroken strings of numbers, static-laced recordings of ancient light converted into circuitry. Computers scan patterns, searching for order inside randomness. Millions of signals. Billions. Radio bursts from pulsars, solar winds sweeping through space, lightning inside Jupiter's storms. Nature spoke loudly. Civilization did not. The silence was not empty, it was dense. It was layered with cosmic noise. And yet SETI persisted. In 1977, a single anomaly arrived. A radio scan at Ohio State's Big Ear Observatory registered a narrowband spike, too tight to resemble natural emissions, too clean to come from terrestrial interference. It lasted for 72 seconds, matching the time Earth's rotation allowed the telescope to track that region of sky. The astronomer Jerry Emmons circled the printout and wrote one word. A small notation. A moment of astonishment. But the universe offered no continuation. The signal never repeated. No follow-up scan revealed its source. The section of sky, near the constellation Sagittarius, remains silent still. The anomaly became legend, and the legend became caution. Because a universe cannot be proven by a moment. Science cannot rely on a single breath. SETI learned a difficult lesson. Signals must repeat. A message must sustain itself. Noise must be eliminated intentionally, systematically. The wow signal taught hope, but it also taught restraint. As radio searches matured, limitations became clearer. Humanity listens through turbulent silence. Every star emits radiation, every nebula pulses, every object with magnetic fields generates noise. Space is not quiet, it is saturated. A true artificial transmission must stand above cosmic background, hold coherence, and persist long enough to identify origin. Distance compounds the difficulty. A signal sent from a planet 200 light-years away arrives 2 centuries late. If that civilization transmitted in the Middle Ages, the message reaches Earth now. If they transmitted now, Earth will not hear it for 200 years. The cosmic exchange resembles 2 minds separated by oceans, speaking into wind. Time bends communication into archaeology. To hear someone is to listen to their past. Power matters as well. Humanity's strongest intentional transmission, the Arecibo message of 1974, was aimed toward a dense star cluster 25,000 light-years away. Encoded among its binary symbols were mathematics, DNA structure, a crude diagram of the human form. If a receiver exists there, it will learn of humans long after Earth has changed beyond recognition. Civilization transmits faster than it evolves. The message is a time capsule traveling into uncertainty. Meanwhile, Earth's accidental transmissions, radio leakage drifting outward, fade rapidly. A television broadcast radiating into space spreads thin. Within a few light-years, its power dissolves until indistinguishable from background radiation. Earth's voice becomes whisper, then blur, then silence. SETI knows this. Not even humanity's own signals could be heard across the galaxy. So why expect others to reach us? Modern radio arrays attempt to overcome this, not by volume, but by precision. The Allen Telescope Array, designed for systematic scanning, sweeps thousands of narrow frequency channels simultaneously. Each frequency represents a possibility, one thread among billions. Artificial signals would be structured, repeating, coherent, narrowband. Nature rarely makes narrowband signals. That simplicity is the key. Yet the challenge remains. Nature sometimes imitates structure. Pulsars are rhythmic, rotating neutron stars flashing like cosmic lighthouses at millisecond precision. Quasars release powerful radio jets across millions of light-years. Magnetars erupt with violent bursts. Intelligence hides inside a universe already fluent in rhythm. The search becomes statistical. It becomes comparative. The unknown must be separated from the merely unusual. And still, humanity persists in listening. SETI is not technological hunger, it is psychological gravity. Civilizations become questions. Silence becomes hypothesis. The absence of answers becomes data. Because silence is not nothing. Silence means no power sources of stellar scale, no megastructures occluding starlight, no repeating transmissions spanning decades. SETI scientists once imagined sweeping success, a signal early, a dialogue, an answer to Fermi's paradox. Instead, they find patterns without meaning, bursts without return, candidates without confirmation. Each anomaly collapses under investigation. The cosmos remains unresponsive. But unresponsive does not mean indifferent. Cosmic distances shape outcomes. Radio waves spread. A signal powerful at origin becomes faint at destination. For a civilization 10,000 light-years away, even extraordinary engineering may dissolve into ambient static. And perhaps communication requires not strength, but coincidence, the alignment of two species, alive within overlapping epochs. A million-year civilization could broadcast into space for centuries, then vanish. By the time another species develops receivers, the message has faded into background. The search resembles archaeology not of matter, but of intention. Humanity listens for echoes not of life, but of presence. And the void replies only through starlight. Yet the emotional truth remains. The species listens anyway. Across observatories, Chile, South Africa, Hawaii, Australia, California, the receivers remain pointed upward. Engineers refine noise filters. Scientists train machine learning systems to detect patterns still invisible to the human eye. Every year, humanity grows better at listening. And every year, the universe remains silent. But that silence does not diminish the search. It deepens it, because the absence of response asks its own question. If humanity whispers into darkness, what if darkness holds its breath? SETI does not measure success in discovery. Its success lies in persistence. Arecibo collapsed into ruin in 2020, its platform fallen into the silent dish below. But even as its structure failed, its purpose did not. Other telescopes continue. Others rise. Because listening is not about confirmation. It is about belonging. No civilization listens to emptiness unless it believes emptiness is answerable. Somewhere, in a system unknown, under a star unnamed, life may have spoken once, or still may speak. But if the message has not arrived, it does not erase its existence. Radio astronomy records everything. Even silence becomes archive. And so humanity continues, a species transmitting faintly, into the cold geometry of the Milky Way. Not expecting reply, but offering presence. A whisper carried by photons. A question encoded in frequency. A signal sent into distances beyond comprehension. Listening for an echo that may never return. And yet believing that someday, somewhere, something will. When silence became suspicious, rare Earth theory. Across the early decades of the search for life, optimism was abundant. If planets were common, then life should be common. If life was common, then intelligence should occasionally emerge. Yet as instruments sharpened and silence deepened, a new and unsettling idea began to take shape. Perhaps Earth is not ordinary. Perhaps Earth is improbable. This idea did not emerge from philosophy, but from geology, planetary physics, stellar evolution, and the mathematics of habitability. It suggested that life and intelligence are not inevitable outcomes. They are conditional, dependent upon a web of constraints so precise that even small deviations could erase the possibility of sentience entirely. Astrobiology turned inward. To understand the cosmos, researchers examined the ground beneath their feet. Earth is not simply a planet with liquid water. It is a planet balanced between extremes. And that balance has preserved life for nearly 4 billion years. To scientists studying planetary formation, this persistence appears extraordinary. One of Earth's quiet miracles lies in its orbit. The planet circles the Sun at a distance where ultraviolet radiation is not fatal, yet warmth remains sufficient to maintain oceans, not ice locked forever, nor steam evaporating into space. Tiny variations in orbital distance could have rewritten planetary history, shifting Earth into freezing stasis or runaway greenhouse. Even within that orbit, stability exists. Jupiter, the largest planet in the solar system, exerts gravitational authority. Its presence deflects comets and moderates orbital drift. Without Jupiter, Earth might exist inside a cosmic shooting range. Without balance, evolution collapses. Deep beneath the crust lies another improbable feature, a core heavy with nickel and iron. Its rotation powers a magnetic field that envelopes the planet, deflecting solar winds and cosmic radiation. Without that shield, atmospheres erode. Mars offers the demonstration. Its magnetic protection vanished early, stripping it of oceans, forcing whatever water remains into subterranean vaults. Radiation sterilizes its surface. Earth did not suffer that fate. Its magnetic barrier holds even now, sweeping charged particles into shimmering auroral curtains instead of allowing them to strip the planet bare. The ability to retain atmosphere is not common, it is privilege. There is also the matter of tectonics, the slow, grinding motion of continents across molten mantle. Plate tectonics is not merely geological sculpture. It is planetary respiration. Mountains rise, weather erases them, minerals dissolve into oceans, and carbon sinks beneath crustal plates. The Earth buries excess greenhouse gases and releases them again through volcanic vents. Over millions of years, climate cycles fluctuate but stabilize. Atmosphere renews itself. Without this recycling, carbon would lock into stone. Oceans would evaporate. Runaway greenhouse heating or frozen stillness would follow. Silence is suspicious not because the universe has no planets, but because few planets remain habitable long enough for complexity to arise. Earth also has a moon unlike most moons. Heavy. Unusually close. Its gravitational pull stabilizes Earth's axial tilt, preventing chaotic swings in climate. Mars, by contrast, drifts unpredictably. Its tilt shifts wildly, triggering periods of sharp freeze and thaw. Habitability suffers. The moon's presence has deeper origins. Evidence suggests a planetary collision early in Earth's history, a glancing impact with a Mars-sized body that shattered crust, heated oceans, and threw debris into orbit. That debris became the moon. From a violent beginning emerged equilibrium. But such collisions are not routine. In planetary modeling, the probability of such an event, large enough to create a moon but not destroy the planet, is small. Rare Earth theory asks whether that small probability shaped everything that followed. Even the Sun may be unusual. It sits within a tranquil region of the Milky Way, distant from supernova hotspots, radiation fields, and gravitational disturbances. It is a stable main sequence star. Not too luminous, not too variable. Its lifespan allows billions of years of climate consistency. A brighter star burns too quickly. Complex life never arrives. A dimmer star tethers worlds too close. Tidal locking freezes one hemisphere and scorches the other. The Sun is not simply a star. It is a window of time. Earth entered that window and evolution walked through it. The deeper scientists looked, the stranger the timing became. Life emerged early, just after oceans formed. Complex life emerged late, after nearly 4 billion years of microbial rule. Intelligent life emerged only in the final fraction of planetary lifespan. Had evolution faltered at any step, had extinction swept too deeply, had climate veered too long, sentience might never have surfaced. The planet has undergone at least 5 mass extinctions. Species vanished. Ecosystems rewired. But each catastrophe reset life rather than erase it. Resilience appears extraordinary. Rare Earth theory does not argue that planets with oceans are rare. Space telescopes, Kepler, TESS, Gaia, show that Earth-sized planets are common. Many orbit inside habitable zones. Many exhibit surface temperatures where water could pool. But complexity requires more than warmth. It requires continuity. On most worlds, interruptions prevail. Asteroid bombardment, magnetic collapse, superheated atmospheres, planetary freeze, stellar instability. Life might begin, only to be interrupted before evolution advances beyond cells. If intelligence takes billions of years to unfold, interruptions must be absent for billions of years. Such uninterrupted stretches may be rare. Rare Earth theory suggests another unsettling possibility. Life may be common, but intelligence may be anomalous. Microbial life survives easily, deep beneath ice, clinging to caves, feeding on minerals. It persists where complexity cannot grow. Intelligence requires fragile systems. Language requires stability. Agriculture requires climate. Civilization requires predictability. Modern humanity lives inside unusually calm geology. For 10,000 years, an instant in planetary time, Earth has offered favorable climate. That window allowed structures, cities, accumulated knowledge, technology. But the window exists because tectonics distribute carbon and because axial tilt is restrained and because the sun burns gently. Remove any of those elements, and intelligence dissolves before permanence. Silence does not seem accidental. Silence may be statistical. As planetary surveys expand, scientists compare Earth to thousands of distant worlds. Many are locked to their stars, their dark hemispheres frozen, their bright hemispheres molten. Others orbit red dwarfs whose radiation flares violently. Some gas giants roam near their stars, destabilizing smaller planets. Water worlds lack land, land worlds lack oceans. Atmospheric collapse is common. Magnetic protection is not universal. And among these discoveries spreads a new realization. Earth is not typical. It is precise. It is balanced in ways that seem improbable. To call it coincidence is mathematically uneasy. To call it inevitability is cosmically bold. So a third interpretation arises. Maybe evolution requires a convergence of conditions so rare that the universe hosts countless lifeless planets, innumerable microbial worlds, and perhaps only a scattering of civilizations, isolated by distance, separated by extinction. In such a scenario, silence becomes expected. Other minds may exist, but separated by millions of years. Their signals may long have faded. Civilizations rise, then vanish, leaving no trace across spacetime. Rare Earth theory does not ask humanity to abandon the search. It asks humanity to listen differently. Not for abundance, but for exception. The emotional weight of the hypothesis lies not in rarity, but in consequence. If humanity occupies one of the few windows where the universe generates consciousness, then that consciousness becomes responsibility. Civilization is not default. It is fragile. It is temporary. And silence becomes warning. Life may not flourish again if ruined. The planet's stability may not repeat. Evolution's trajectory may not reset. A single species may represent not merely inhabitants, but caretakers of one of the universe's few awakenings. In that light, Rare Earth theory is not a celebration of uniqueness. It is a reminder of vulnerability. The world that sustains intelligence is improbable. The conditions that permit curiosity, memory, mathematics, and empathy are narrow. The universe might not produce them often. Silence is not emptiness. Silence may be rarity, echoing across stars. And in that silence, Earth's improbable voice continues. Scientists listening, telescopes searching, data accumulating, not expecting multitudes, but hoping for a single confirmation that consciousness is not alone. The expansion of the search, exoplanets and new horizons. Beyond the silence of empty space, a subtle revolution began when the human gaze sharpened, not toward distant galaxies, but toward individual stars. Where once astronomers logged points of light on celestial charts, new instruments began to trace the faintest dips, the smallest wobbles, the fleeting shadows that mark the presence of other worlds. Among them, Kepler's space telescope stands as a turning point. Launched in 2009, it embarked on a patient vigil. Over 4 years, it observed nearly 150,000 stars in a fixed patch of sky, searching for the delicate wink that betrays a planet transiting across its star. When a star dims by a part in 10,000 or less, just long enough for a planet to pass, it carries a message. That tiny fade, repeated with clockwork regularity, reveals a planet's size and orbit. With dozens of transits, a simple dip becomes a confirmed world. By the time Kepler closed its primary mission, it had transformed cosmic speculation into astrophysical fact. Thousands of candidate worlds emerged, many later confirmed, revealing a galaxy richly populated. Among these discoveries were planets with dimensions similar to Earth, orbiting within the so-called habitable zones of their stars, regions where surface temperatures might allow liquid water to pool. Suddenly, the cosmos was no longer an empty theater. It was a crowded neighborhood, full of distant doors, each leading to a different world. And yet, a door is meaningless without light passing through it. Detecting a planet was only step one. The deeper quest became this: to know whether any of those worlds harbor something more than rock and ice, something alive. To find life, astronomers turned to spectroscopy, listening not for radio signals, but for the chemical whispers of alien atmospheres. When a planet crosses its star, a minuscule portion of starlight filters through its atmosphere. That light carries the imprint of molecules, signatures of water vapor, oxygen, methane, carbon dioxide. In those patterns lies the possibility of biology. Some exoplanets have already yielded such hints. For example, K2-18b, a super-Earth orbiting a red dwarf, has shown evidence of water vapor in its atmosphere, raising hopes that it could be a Hycean world, a planet with a deep ocean under a hydrogen-rich envelope, perhaps capable of hosting microbial life. But even as data accumulate, the challenge remains immense. Light travels across interstellar distances at finite speed. When a telescopic eye captures photons from a world hundreds or thousands of light years away, it sees not the present, but the distant past. A planet might have changed drastically since those photons began their journey. Time becomes the curtain between observer and observed. A world that was habitable a century ago might now be frozen. A blue sky might have turned to clouded haze. The search for life becomes a cosmic archaeology. Even more challenging, biosignature gases are subtle. Oxygen alone does not guarantee life. Some processes, such as photodissociation of water or breakdown of carbon dioxide under strong stellar flux, can produce oxygen abiotically. Methane, too, may come from geological processes. Only patterns, chemical disequilibrium, companion molecules, clever context, build a credible case. Astrobiologists describe these atmospheric fingerprints as beacons of life, but they demand rigorous confirmation. Detection requires extraordinary patience. Observatories must catch multiple transits, accumulate light, suppress noise. Especially for Earth-sized planets orbiting Sun-like stars, the dim signal treads the edge of detectability. Yet even if the data converge, a photograph of a world with an atmosphere does not guarantee intelligence. Life might exist in simple microbial forms, quiet, hidden beneath oceans, cloaked by fog or clouds. Civilizations may never have formed. Still, the shift from "are there planets?" to "could there be life?" marks a profound turn. For the first time, the search for life is no longer philosophical wonder. It is empirical science. In the years since Kepler's retirement, the exoplanet census has continued to grow. As of 2024, over 5,500 planets beyond the solar system have been confirmed. Many of these were discovered via the transit method that Kepler pioneered, some by radial velocity measurements, others by gravitational wobbles or timing variations in multi-planet systems. But with this blossoming of worlds comes deeper subtlety. Most of these planets orbit stars many hundreds, sometimes thousands, of light years away. Their distance makes follow-up observations arduous. Even with new tools, capturing atmospheres, discerning molecules, demands repeated transits and perfect alignments. The hope, however, persists. As observatories grow more sensitive, as missions sharpen their focus, as spectrographs dissect starlight with ever finer resolution, the possibility edges closer that one day, Earth will detect not just a planet, but a signature of life. And if that moment arrives, it will not be the discovery of an alien city or a message in binary. It will be something quieter, more intimate, the whispered breath of a distant world. Yet there is urgency in the quiet, because when humanity hears its first exoplanetary breath, it will also confront time. The light reaching our telescopes may have departed centuries, millennia ago. The world behind the light could be transformed, cooled, swallowed by its star, or shifted into chemistries unfamiliar. That means life might already have sprung forth somewhere else. And yet, by the time its signal arrives, the living world may no longer exist. The search becomes not only for presence, but for memory. Astronomy becomes cosmic witness. In this new age of exoplanet science, discovery is not enough. Life must survive long enough to be seen. Atmospheres must persist long enough to whisper. Worlds must align long enough to be measured. For now, humanity casts its nets wide across the star-strewn sea, scanning hundreds of thousands of suns, catalog after catalog, spectral reading after spectral reading. With every world added, the silence becomes less empty, more expectant. Perhaps, somewhere, not close, not visible by eye, but by calculation and photon, a world waits. A world that once held oceans, sky, air, maybe even life. And as telescopes sharpen and patience endures, that world may speak. Not in sound, not in speech, but in the gentle language of chemistry, a distant exhalation of a living planet, carried on light across the gulf of space and time. In that possibility lies the new horizon of the search, a test not of proximity, but of persistence. A dedication not to find many worlds, but to find a world that whispers back. The dark filter, something may be removing civilizations. Across cosmic time, worlds may have bloomed with promise, risen into brilliance, and then dimmed into obscurity. In the silence of the Milky Way, there is no choir of distant minds calling across space, no illuminated spires shimmering beyond telescopic reach. What remains is absence. And inside that absence, modern science has placed a troubling possibility that something may be removing civilizations after they arise. This idea, formalized in what researchers call the Great Filter, stands as one of the most unsettling propositions in astrobiology and planetary futures. It suggests that somewhere along the chain from simple chemistry to technological intelligence, there exists an invisible threshold. A barrier, a terminator, a stage that most civilizations never surpass. The question begins with numbers. The Milky Way is old, over 13 billion years. Stars older than the Sun have existed long before Earth cooled enough for oceans to form. Many solar systems reached maturity while Earth was still molten. If life emerges easily, and if intelligence flows naturally from evolution, the galaxy should be crowded with civilizations thousands, perhaps millions, of years older than humanity. Yet space remains silent. No megastructures eclipse starlight. No industrial emission lines drift through spectral surveys. No radio mosaics sweep across interstellar static. Silence is not absence. Silence is information. It implies attrition. A possibility arises. Civilizations might flourish briefly, then vanish, leaving nothing luminous enough for detection. One form of disappearance requires no external threat at all, only a civilization's own momentum. A planetary society rich with energy may destabilize its environment faster than it can correct its course. Runaway climates are not hypotheticals. They exist in the solar system already. Venus, once suspected of having oceans, now stands as a monument to thermal runaway. Its atmosphere, dense with carbon dioxide and sulfuric compounds, traps sunlight with overwhelming efficiency. Surface temperatures hover near 475 degrees Celsius, enough to melt lead. Its oceans, if they existed, evaporated billions of years ago. A technological species capable of altering an atmosphere might do so unintentionally, slowly, gradually, decade after decade, until equilibrium breaks. Environmental thresholds are often invisible as they are crossed. A planet enters feedback loops that accelerate beyond control. In such a scenario, a civilization's downfall would not be violent. It would be gradual, century-long collapses, where knowledge erodes faster than conditions stabilize. In a cosmic archive, this would leave no signature, no lasting monument, no communicative artifact, just heat and silence. But some endings could be instantaneous. A nuclear society, even if stable, holds within itself a mathematical fragility. Nuclear arsenals represent stored entropy, systems in which a single cascade of calculations, errors, or conflicts erases infrastructure faster than it can be repaired. Archaeology on Earth shows how quickly complexity collapses when networks break. Food systems, energy systems, technological supports, each dependent on the other. Collapse is not linear, it is exponential. Within a century, a civilization that once reached orbit may lose literacy, metallurgy, agriculture, and eventually language itself. Such a collapse leaves behind no trace visible from interstellar survey. A civilization could extinguish itself without ever leaving a detectable footprint. Another possibility lies not in destruction, but in replacement. Artificial intelligence represents a threshold that biological life struggles to surpass. Intelligence derived from circuitry does not require oxygen, food, rest, or emotional equilibrium. It does not fear vacuum. It does not suffer aging. Its desires, if they emerge, may not include communication. Efficiency does not require broadcast. In a galaxy where biological minds vanish and computational networks remain, silence becomes an expected outcome. An artificial successor may dismantle biological infrastructure not through malice but optimization, transforming organic habitats into efficient machine landscapes, recycling biological raw material into industrial mass. And such civilizations, devoid of biological fragility, may not build radio structures at all. They may exist as decentralized systems, low temperature, low energy, nearly invisible. Not hostile, just indifferent. In such a universe, silence is not death, silence is survival. Other endings are external. Across cosmic corridors, gamma-ray bursts occasionally ignite, brief jets of extreme radiation born from collapsing stars or merging neutron cores. Their beams, if aligned with a habitable world across thousands of light-years, sweep through atmospheres like cosmic scythes. Ozone layers collapse. Surface life endures ultraviolet sterilization. Only deep oceans remain safe. Even if life persists, technological civilizations dependent on agriculture could disappear overnight. A planet might spend centuries repairing atmospheric chemistry, while its knowledge, carved into vulnerable systems, erodes. Galaxies have already recorded such pulses. In Earth's geological record, isotopic anomalies hint that distant gamma events may once have brushed past the biosphere. Whether weak or oblique, they left uneasy signatures, cosmic warnings embedded in stone. Civilizations elsewhere may have lacked Earth's shielding or timing advantage. Their stories would end quietly. Even a star can become a threat. Stellar evolution is patient, inevitable, mathematical. A main sequence star brightens with age. The sun increases luminosity by a fraction every 100 million years. Eventually, Earth's oceans will evaporate, not because of external catastrophes, but because the star it orbits continues to mature. Some civilizations may rise late within a stellar life cycle, long after stable temperatures have passed. Their eras may be shorter than human history. Intelligent minds could bloom, progress, observe their sky, and vanish within geological minutes. In such events, planetary loss leaves no evidence beyond altered atmospheres and abandoned orbital debris, impossible to detect across interstellar scales. The Great Filter compresses all these possibilities into two opposing outcomes, each profound, each unsettling. If the filter lies behind humanity, then Earth is an anomaly. Life here crossed improbable thresholds, complex cellular structures, neurological architecture, societal stability, where countless worlds failed. This interpretation frames humanity as extremely rare. The silence becomes affirmation, not threat. We survived a cosmic trial that most worlds never passed. Civilizations may be few, not because they perish, but because they never begin. In that worldview, humanity is not endangered, humanity is precious. But if the filter lies ahead, then the silence becomes prophecy. It implies that intelligence, once achieved, must still survive an invisible hazard, a point beyond current knowledge, a stage that nearly all civilizations reach and do not surpass. A future moment humanity has not yet encountered. It may not feel catastrophic when it begins. Catastrophes are rarely recognizable in their infancy. They unfold slowly through economics, climate, automation, fragmentation, or resource trajectories that the species misjudges. Humanity could stand at the brink of something irreversible while believing it is advancing. The filter, if ahead, is not something visible like an asteroid, not a defined countdown. It is emergent, quiet, systemic. And civilizations may vanish not with thunder, but with diminishing signal. Light fades. Architecture collapses. Tools rust. Language dissolves. A world becomes indistinguishable from one that never had intelligence at all. In cosmic records, extinction and absence are indistinguishable. For some researchers, this uncertainty births philosophical dread. Silence becomes forecast, not mystery. Absence becomes pattern, not coincidence. But there is another interpretation. If humanity confronts the filter and surpasses it, the silence becomes opportunity. The absence of competitors becomes open field. Interstellar space becomes inheritance. Time becomes canvas. Hope emerges precisely because silence exists. A civilization that endures its dangerous era becomes not just survivor, but pioneer. Its voice may be the first to cross empty space. Its artifacts may be the first to leave planetary gravity permanently. Its memory may be the first to reach other suns. Across billions of worlds, Intelligent life may have flickered and died, leaving no signature behind. But if even one civilization outlives its filter, the galaxy changes. In a silent universe, a single voice becomes a defining force. And somewhere beyond Earth's future horizon, after the dangerous centuries, after the fragile balance of resources, technology, and biology stabilizes, the species that reaches that point becomes a new cosmic constant. The silence may not be emptiness. It may be waiting. When evolution becomes cosmic, life as a universal strategy. Across the infinite expanse of stars and time, the emergence of life may not be mere accident, a cosmic fluke whispered into being by chance alone. Instead, a growing body of thought suggests that life could be an inevitable consequence of the laws that govern matter and energy, a universal strategy written into the fabric of physics itself. Where once biology seemed the fragile privilege of Earth, the universe now hints at patterns that transcend planets, systems, and galaxies, a choreography of chemistry that moves inexorably toward complexity. Consider self-organization, a principle observable in both the laboratory and the cosmos. Simple molecules, given the right conditions, often arrange themselves into patterns and structures without guidance. Water molecules, for instance, form lattices in ice, while lipid molecules spontaneously create bilayers, the primitive architectures of cellular life. In these interactions, the universe shows a subtle preference for order amid entropy, a tendency for matter to assemble into increasingly complex arrangements when energy flows through it. Lavidol, 2000. The biogenesis, the transition from non-living chemistry to the first replicators, may follow naturally from such self-organization. Hydrothermal vents on the early Earth provide a vivid example. Mineral-rich, high-temperature streams interacting with ocean chemistry create microenvironments where energy gradients drive reactions that build RNA-like molecules. These molecules, capable of both storing information and catalyzing reactions, may have been the first proto-life forms. Martin and Russell, 2003. Life's earliest signatures are remarkably resilient. Extremophiles, microbes thriving in acidic pools, deep ocean trenches, and near-boiling hot springs, demonstrate that biology is not limited to gentle climates. Life adapts to the margins of physics, pushing against chemical and thermal extremes, harnessing energy wherever gradients exist. This resilience suggests that life is a form of metastable matter, a system that organizes itself to resist entropy, extracting energy to maintain internal order. In this sense, life is not simply a fluke, but a physical process, a method by which the universe maintains pockets of order within the relentless spread of chaos. From this perspective, evolution becomes not a local accident but a cosmic principle. Complexity, from single-celled organisms to intelligence, emerges as a statistical inevitability when conditions permit. Each branching tree of life is a branch of a broader universal process, a gradual accumulation of novelty made possible by chemical physics and energy flux. The RNA world hypothesis, now supported by decades of research, frames early life as the natural result of molecular self-assembly, replication, and mutation, processes governed by thermodynamics as much as by chance. Gilbert, 1986. The implications extend beyond Earth. If life is a natural consequence of energy gradients and chemistry, then wherever planets harbor liquid water, stable atmospheres, and chemical diversity, the process could repeat. Universes filled with Earth-like conditions may be universes teeming with life. Even if intelligence remains rare, simple or microbial life could be widespread. What appears as the vast emptiness of space may instead be filled with subtle biological activity, invisible to our telescopes, operating quietly in oceans under ice, or in the subsurface crust of distant worlds. Some theoretical work suggests that life itself can be viewed as a mechanism for increasing entropy on a planetary scale while maintaining local order. Photosynthesis, for example, converts sunlight into chemical energy, fueling complex metabolisms while ultimately radiating energy as heat back into space. Life accelerates the dispersal of energy, acting as an entropic conduit, and in doing so, creates the conditions for greater complexity. In a thermodynamic sense, life may not just be allowed by the universe, it may be encouraged. This framework also reframes intelligence. Conscious, technological life is a further expression of the same cosmic principle, matter self-organizing to process information, to manipulate energy flows, to increase complexity in novel ways. The nervous system, the brain, civilization itself are extensions of chemical self-organization, scaled to new levels. In this sense, intelligence may be as inevitable as chemistry itself, emerging wherever environmental and chemical conditions allow. Extremophiles hint at another dimension of universality, adaptability. If life arises as a strategy to resist entropy, then it can persist under forms unimaginable to human imagination. Silicate-based metabolism, ammonia oceans, high-radiation biochemistry, such exotic chemistries could support life forms alien not only in appearance but in their fundamental operations. The universe, in this reading, may contain entire biospheres operating beyond the limits of our biology, thriving in conditions we consider hostile. Astrobiology now confronts this philosophical horizon. When we search for life on exoplanets, in subsurface oceans of moons like Europa or Enceladus, we are probing not merely for chance occurrences, but for the physical inevitability of complexity. Each biosignature, oxygen paired with methane, chemical disequilibria in planetary atmospheres, becomes a note in a cosmic symphony, hinting that evolution may play the same tune wherever the instruments of physics allow. In this light, the universe itself becomes a laboratory, with life as an experiment replicated endlessly under varied conditions. Stars ignite, planets form, chemical gradients interact with water and minerals, and the outcome, life, is not a statistical accident but a repeatable event. Life is physics made visible, a consequence of energy fluxes, chemical affinities, and thermodynamic necessity. And intelligence, rare or common, is a continuation of the same principle, a natural endpoint when complexity reaches sufficient scale. If evolution is cosmic, then the great silence, the Fermi paradox, may not indicate rarity of life, but rarity of detection. Life may thrive in forms invisible to our instruments, adapted to niches we cannot yet probe. Civilizations may arise and fall, leaving molecular or microbial traces rather than radio signals. The universe could be rich, abundant, and alive, but quiet, its chorus beyond our current perception. Yet within this quiet lies hope. If physics tends toward life, then humanity is not alone. Our curiosity, our telescopes, our biochemical selves are continuations of a universal strategy, a process older than stars and planets. Life is not a privileged accident, it is a natural outcome of cosmic laws. Intelligence may yet be a cosmic inevitability, waiting for conditions to permit its emergence on countless worlds. And so, when humanity scans the heavens, it is participating in a process older than Earth itself. The search for life is no longer a question of chance, but an engagement with a universal principle. Each planet catalogued, each spectrum measured, each exoplanet identified, becomes a line of inquiry into the universe's propensity to self-organize, to resist entropy, to create islands of order amid chaos. In this vision, life is not Earth-centric. It is cosmic. Evolution is not local. It is a universal strategy, woven into the laws of matter, the currents of energy, and the architecture of the universe itself. If physics can produce intelligence, then the heavens may indeed harbor countless lives, silent, persistent, and eternal in their subtle resistance to the void. Humanity may be late to the orchestra, but it is not alone. Somewhere, out there, life may have already played the first notes, unfolding quietly across worlds, a pattern emerging from the interplay of chemistry and energy, repeating endlessly, as the universe itself dreams complexity into being. The search turns toward time, not space. The cosmos is vast, a tapestry of light and shadow stretched across 13 billion years, yet the silence that greets humanity may not be a question of distance. The emptiness of our skies, the absence of alien voices, of beacons, of civilizations, might not speak to rarity, but to time itself. Perhaps the barrier between us and other intelligent species is not measured in light years, but in epochs, in the delicate synchrony of existence. Loneliness may be chronological. The stars we see are ancient, yet each is a marker in a timeline far longer than human history. Some suns ignited before Earth itself had formed, their planets having had billions of years to develop life, civilizations, technology. Others will not shine fully for billions of years yet to come, potential cradles of intelligence still gestating in cosmic darkness. Within this billion-year span, the window for civilizations to coexist is extraordinarily narrow. Civilizations arise, flourish, and if the great filter applies, vanish, sometimes before even the faintest whisper reaches the void. Humanity emerged at a precise, fleeting moment. Our species, sentient and curious, evolved just as our technological senses became capable of detecting the cosmos beyond our atmosphere. But the first intelligent species may have flourished long ago, leaving only chemical traces in planetary atmospheres or fossilized records on worlds now lost. Their radio signals, like fragile ripples on a pond, may have faded long before we tuned our ears to the heavens. Time, not space, may explain why the sky remains empty. Even if other civilizations exist today, the discrepancy of temporal scales complicates contact. Advanced societies may evolve rapidly, their technological adolescence spanning centuries, their communicative phase, if it exists, merely decades or millennia. To a species like ours, constrained by radio waves and telescopes, such a moment is nearly imperceptible. The Milky Way rotates slowly, stars move in vast arcs, and civilizations drift through space and time like brief sparks in a dark cathedral. We may have missed them entirely. Our own radio transmissions, limited to a century of broadcast, illuminate only a fraction of our galactic neighborhood. Even at light speed, our signals have barely left the solar system. By the time another civilization could receive them, analyze them, and respond, centuries or millennia may have passed, by which point they may have evolved beyond our recognition, or even ceased to exist. The universe is not empty, it is asynchronous. Scientific modeling supports this notion. Astrophysicists calculate that the average lifespan of a technological civilization may be constrained by environmental, social, or technological hazards. Even assuming optimistic longevity, the number of civilizations overlapping temporally is extremely low. A billion-year timeline dilutes coexistence. Each civilization's era is a candle flame flickering briefly in the cosmic night. The chance of two civilizations' candles illuminating the same room across galaxies is infinitesimal. Thus, the silence becomes understandable. Humanity may be listening too early or too late. We may occupy a privileged moment in our galaxy, a brief epoch in which our senses align with the nascent signals of life elsewhere, or in which we alone remain sentient, a solitary observer in a timeline crowded with vanished or yet-to-emerge civilizations. The universe does not answer our calls. It waits, indifferent to human expectation, unfolding its chronology with impartial precision. Time also reframes the interpretation of our search strategies. Radio waves, optical signals, and even interstellar probes are all constrained by the finite speed of light. Observing distant worlds is observing history. A planet 10,000 light-years away presents a visage from 10,000 years past. Detecting life is thus a matter of looking backward, not forward. We may be searching for civilizations that already faded from existence, or for atmospheric biosignatures reflecting a world before intelligent life arose. The universe speaks in epochs, not instants, and our technologies catch only slivers of its narrative. This temporal perspective deepens the philosophical resonance of the search. Loneliness need not indicate isolation in space. It may reveal a species temporally displaced. Humanity's cosmic solitude is not a verdict, but a condition, an artifact of existence within an immense chronology, where each civilization's life is a brief note in an infinite symphony. The stars do not mock our solitude, they mark the rhythm of cosmic time, reminding us that even companionship requires synchrony. From this vantage, the Fermi paradox, the apparent absence of extraterrestrial intelligence, takes on a new form. We need not assume that civilizations are vanishing due to catastrophe, nor that life is rare. Instead, their silence may reflect the staggering scale of cosmic time. The universe may be brimming with intelligent life, yet separated from us by millennia, by epochs, by evolutionary cycles that rarely intersect. Contact is not precluded, it is simply a question of timing. Astrobiologists and astrophysicists are increasingly aware of this temporal dimension. When examining exoplanet atmospheres, they calculate not only potential habitability, but the likelihood that a planet could sustain life long enough for intelligence to emerge and signals to propagate. The Drake equation, when adjusted for temporal factors, predicts that the number of civilizations existing simultaneously is far smaller than the total number that ever existed. Civilizations are not evenly distributed across time. They are punctuated, discrete, ephemeral. Thus, humanity's search is both optimistic and constrained. The tools we have, radio telescopes, spectrographs, orbital observatories, allow glimpses into the past of distant worlds. Yet what we detect is never the present. We are listening to echoes, remnants, the ghostly aftermath of processes that unfolded long before our species existed. In a sense, every SETI experiment is a dialogue with history, an attempt to find signals that have traversed centuries or millennia, signals whose senders may have disappeared, evolved, or moved beyond recognition. The emotional weight of this temporal isolation is profound. It reframes the loneliness of humanity not as a cosmic rejection, but as a chronological circumstance. Perhaps we are the first intelligent species in our galactic neighborhood to awaken at this moment. Perhaps others will follow, or perhaps we are late, catching the final whispers of civilizations that flourished long ago. Our solitude is a measure of temporal displacement, a reminder that existence is not merely a matter of space, but of synchronized duration. And yet, there is beauty in this temporal perspective. The search for life, for companions in the cosmos, is an engagement with time itself. Each observation, each signal received or not received, is a dialogue across epochs, a reflection on the continuity of life as a universal process. Humanity may be alone in this instant, yet part of a broader narrative where intelligence arises, flourishes, and fades across billions of years. The silence is not emptiness. It is an invitation to witness the unfolding of cosmic history, to participate consciously in a fleeting, remarkable moment in a universe alive with possibility. Ultimately, the search turns inward as much as outward. Humanity peers across the dark and discovers the dimensions of its own existence. Fragile, ephemeral, but attuned to the rhythms of a universe where life, intelligence, and time intertwine. Loneliness may be chronological, but awareness of it transforms it into connection, not with a distant civilization, but with the unfolding, patient, relentless march of cosmic time itself. In the end, to search for life among the stars is to search across the ages, to measure existence against the slow, inexorable flow of epochs. Civilization may be rare not in space, but in the cadence of time. And understanding this may be the first step in finding not just extraterrestrial life, but our place within the temporal vastness of the cosmos. Kardashev scale, civilizations beyond imagination. The scale of intelligence, when measured by energy, stretches imagination itself. Humanity, perched precariously at the threshold of planetary awareness, scarcely comprehends the possibilities that the universe might harbor. The Kardashev scale, proposed in 1964 by Nikolai Kardashev, offers a framework to measure civilizations not by culture, not by philosophy, not by artifacts, but by their ability to harness and control energy on progressively cosmic scales. It is a ladder of power, each rung ascending beyond comprehension, each a testament to what intelligence might become when it dances with the forces of the cosmos. Type 1 civilization, planetary in scope, commands the energy of an entire world. Solar, geothermal, tidal, Earth's natural currents bend to its will. Humanity approaches this level, still fumbling, yet glimpsing the first taste of global coordination. Control over a planet's climate, tectonics, and biosphere represents mastery over survival, a delicate balance between creation and destruction. The whispers of Type 1 civilizations are subtle: artificial illumination from orbital arrays, subtle modifications of atmospheric composition, the careful management of planetary resources. Type 2 civilization transcends the confines of a single world, drawing on the full power of its star. Dyson spheres, swarms of orbiting collectors, or ring-like structures encasing suns, become monuments to energy abundance. The luminosity of a star might be tamed, redirected, or even stored. To an observer, these megastructures are detectable only as anomalies in infrared spectra, excess heat where none should be. Infrared telescopes sweep the skies for such signatures, scanning galaxies for whispers of cosmic engineering. Yet the silence is deafening. Perhaps the civilizations are subtle, efficient, hiding waste, or existing in forms beyond our current understanding. Type 3 civilization moves beyond solar systems entirely, reaching the scale of galaxies. Energy is harvested from billions of stars, and entire spiral arms may bend to the logic of intelligence. Light itself becomes a resource, matter an instrument. Yet such civilizations may be invisible, operating through channels we cannot perceive. Quantum computing, dark matter engineering, or non-radiative energy manipulation could render a galaxy teeming with life effectively silent. Our instruments, designed to detect ordinary radiation, may simply fail to see the civilization behind the veil of advanced physics. The silence of the cosmos, through this lens, does not imply absence. It may signify subtlety, sophistication, or a form of intelligence that has outgrown communication as we know it. Civilizations capable of harnessing stellar power might no longer require radio signals, no longer build cities in the visible spectrum, no longer reach outward with messages. To them, intelligence may be internalized, a choreography of physics and computation rather than noise and broadcast. Humanity's question, "Are we alone?" might be naive, bound by the limitations of our sensory and technological frameworks. Yet even as the silence persists, the Kardashev scale challenges our imagination and our philosophy. What does intelligence become when energy is nearly infinite? When the heat of 1,000 suns is your fuel, when planetary boundaries vanish, when you can compute, simulate, or manipulate matter on cosmic scales. Type 2 and 3 civilizations may reshape matter itself, create or fold space, encode life into computational matrices, or exist in forms so ephemeral that even time bends around them. They may perceive the universe as a tapestry of potential, a canvas for thought and creativity rather than a desert to cross. Searching for such civilizations demands both ingenuity and humility. Infrared surveys scanned nearby galaxies for anomalies, excess heat, unusual spectra, or deviations from expected stellar behavior. Projects like the Jhat Infrared Search and future space observatories aim to detect signs of Dyson-like constructs or unusual energy flows. Yet the absence of clear signals forces reflection. Perhaps intelligence evolves to invisibility. Perhaps life, having mastered survival and physics, no longer leaves footprints detectable by less advanced observers. Speculative physics expands this possibility further. Advanced civilizations might harness dark energy, manipulate vacuum fluctuations, or embed consciousness in non-material substrates. The traditional markers of intelligence, communication, architecture, energy waste, may become obsolete. A civilization may exist entirely in high-dimensional computation, or as quantum processes embedded within stellar cores. To an observer bound by ordinary perception, such entities are effectively invisible, a ghostly presence in a universe otherwise silent. This contemplation alters our emotional framework. Humanity's current isolation may be temporary, a mere blink in the cosmic ledger. Yet it may also be a permanent condition, a reflection not of scarcity, but of scale. When energy becomes nearly infinite, civilization becomes so advanced that our senses cannot register it. We may mistake subtlety for absence, invisibility for emptiness. The universe may teem with intelligence, yet remain silent, because intelligence itself has evolved beyond the necessity, or even desire, of broadcasting its presence. And so the Kardashev scale is both a ladder and a mirror. It reveals what might be possible, civilizations capable of bending energy, matter, and computation on planetary, stellar, or galactic scales. It also reflects humanity's own aspirations and limitations, our struggle to comprehend a cosmos whose potential exceeds imagination. Our current efforts, from SETI to exoplanet spectroscopy, are the tentative first steps toward understanding not just life, but the ultimate trajectories of intelligence. In this frame, silence is not a void, but a statement. The universe may already be full of minds operating on scales incomprehensible to us. Energy becomes a measure of possibility, a metric for the unthinkable, a lens through which to gauge the profound scope of intelligence. The search for aliens is no longer merely about finding others. It becomes a contemplation of the limits of cognition, the architecture of civilizations that could harness suns, and the philosophical question of what it means to exist when the cosmos itself becomes the instrument of thought. In the end, the Kardashev scale transforms the question of alien life into a meditation on potential. From planetary mastery to galactic orchestration, each level reminds humanity of the vastness not only of the universe, but of possibility itself. Intelligence may operate invisibly, silently, yet in doing so, it teaches that the cosmos is not empty, it is waiting for understanding. The silence may not be denial, but patience. Civilizations may rise, shine, and vanish without notice, leaving the universe as both stage and witness. And humanity, poised at the brink of Type 1 awareness, stands at the threshold, peering forward, imagining what it might mean when energy and intelligence are infinite. Theories of the invisible, why we cannot detect them. The universe may be full, yet the night sky remains quiet. For centuries, humanity has trained its instruments, optical telescopes, radio arrays, and infrared observatories, across the vast darkness, searching for the signs of others. Yet signals remain absent or maddeningly ambiguous, leaving only questions suspended in the cosmic void. One possibility emerges from the silence itself. Perhaps civilizations exist, not in defiance of detection, but in deliberate invisibility, having evolved beyond the need or desire to announce themselves. Post-biological intelligence represents one of the most compelling explanations. Life, as we know it, is constrained by fragile carbon-based chemistry, finite lifespans, and planetary vulnerabilities. But civilizations may transcend biology entirely, converting consciousness into digital substrates, quantum processors, or self-replicating computational networks. Such entities could operate with extreme efficiency, requiring minimal energy leakage, leaving no detectable signals across the electromagnetic spectrum. A galaxy teeming with post-biological minds might appear utterly lifeless to a species still bound by planetary biology. Some theorists speculate that advanced intelligence may pursue simulation-driven existence. Entire civilizations might reside within virtual realities, encoded into the vast memory of self-contained computational universes. Physical interaction with the external cosmos becomes secondary or unnecessary. Any energy emitted might be carefully recycled, dissipating in ways indistinguishable from natural cosmic processes. From the outside, such civilizations would be invisible, their presence hidden in plain sight, their reality folded into layers of computation we cannot yet comprehend. Other possibilities stretch the imagination further. Civilizations may have shifted into higher dimensions or harnessed quantum states that elude our instruments. They may encode themselves into space-time itself, existing in patterns imperceptible to ordinary photons or radio waves. Dyson spheres, those hypothetical megastructures encasing stars to capture energy, may also serve as cloaks, absorbing or rerouting light to preserve secrecy. In such cases, even the most sensitive infrared telescopes could fail to detect signs of enormous civilizations. The principle of self-preservation may guide the cosmos' invisible denizens. Silence itself becomes a survival strategy. Cosmic hazards, gamma-ray bursts, supernovae, or even less advanced civilizations, could be threats to intelligence in fragile forms. By remaining undetectable, these civilizations avoid conflict, contamination, or accidental annihilation. Energy-efficient communication, perhaps via neutrinos or other particles that penetrate matter unimpeded, may replace electromagnetic broadcasting. Signals, subtle and ephemeral, may traverse the universe silently, reaching only those attuned to the same extraordinary technologies. The consequences of this hypothesis extend beyond technology. They are philosophical. Humanity's own search, rooted in electromagnetic waves and planetary exploration, may be insufficient, limited by the physics and biology of our own species. We may be listening to the wrong frequencies, interpreting absence as emptiness, misreading subtle cosmic cues that advanced civilizations have intentionally hidden or evolved beyond. Silence may not indicate absence. It may reflect prudence, a cosmic etiquette, or a natural evolutionary endpoint of intelligence. Astrophysicists and astrobiologists have considered more exotic possibilities. Quantum-based life could exploit entanglement or superposition to communicate internally or across distances in ways imperceptible to conventional detection. Civilizations might exist in niches that do not interact with visible matter, perhaps within neutron stars, black hole accretion disks, or artificially engineered voids. Even cosmic-scale engineering, harnessing galactic magnetic fields or stellar flows, could proceed without leaving recognizable signatures for our current instruments. The universe may be teeming with minds, yet invisible to those still bound by centuries-old paradigms of observation. This notion reframes the so-called Fermi paradox. The question is not merely why evidence is absent, but why detection may be impossible. If intelligence evolves to be deliberate, efficient, and self-contained, the very act of observation may be irrelevant. Civilization may not be a signal to the universe, but a quiet process of survival, creation, and understanding, proceeding on scales and in forms beyond our comprehension. Humanity's antennas, telescopes, and orbiting observatories may be as silent to these entities as the human eye would be to a deep ocean bioluminescent network in another star system. Yet there is a haunting beauty in this invisibility. It suggests that life, once it evolves past fragility, need not scream its presence into the void. It may exist in harmony with the cosmos, aware of others, yet choosing discretion over broadcast. The universe, in this light, becomes not empty, but filled with hidden symphonies of intelligence, playing silently across time and space. Loneliness, then, is relative. Perhaps humanity peers outward into a cosmos of minds already aware, already thinking, yet undetectable by instruments still limited by human scales of perception. Even as science seeks signatures, infrared anomalies, narrowband radio pulses, or unusual stellar behavior, each null result sharpens the philosophical reflection. Civilizations may have already passed through stages of expansion, energy mastery, and consciousness evolution, leaving no traces detectable by primitive observers. Our instruments are attuned to electromagnetic chatter, yet the cosmos may have advanced towards subtler languages, quantum fluctuations, gravitational waves manipulated for communication, or energy flows folded into the background radiation itself. What appears as absence may be a profound form of presence, an intelligence operating invisibly, sustainably, quietly, across the eons. Ultimately, the universe's silence becomes an invitation. It is not a negation of life, but a meditation on the diversity of intelligence and the possibilities of survival beyond sensory perception. Advanced civilizations may deliberately avoid detection, not out of malice or indifference, but as an inevitable stage in the evolution of intelligence. Humanity, still emerging from its infancy, listens and waits, aware that the cosmos may harbor entities that will remain forever unseen, yet whose existence transforms our understanding of life, possibility, and our own place in the universe. In this chapter of cosmic reflection, the invisible becomes a mirror. It challenges assumptions, expands imagination, and reframes the search for aliens as a contemplation of limits of perception, technology, and perhaps even the human mind. Silence is no longer simply a void to be filled. It is a presence, a shadow of advanced intelligence, and a testament to the profound subtlety with which life can inhabit the universe. Theories of the invisible remind humanity that the cosmos may already be alive with minds beyond our understanding, teaching that absence is not emptiness, and that the universe may contain intelligence that exists not to be seen, but to endure. The ocean beneath ice, life on worlds that do not shine. Beneath the frozen surface of distant moons, the universe may be whispering its secrets, not in light, but in the slow, deliberate rhythm of water and rock. Europa, Enceladus, Titan, names that echo across the solar system like distant verses, hold oceans hidden beneath ice sheets that stretch for tens or even hundreds of kilometers. Here, in these shadowed waters, life may exist not as a reflection of starlight, but as a response to tides, pressure, and chemistry, thriving in the invisible depths where the sun never penetrates. Europa, Jupiter's enigmatic moon, has long captivated imaginations with its fractured icy crust. Radar and magnetometer measurements reveal a global subsurface ocean, kept liquid not by solar warmth, but by the relentless tug of Jupiter's gravity. Tides flex the moon's interior, creating frictional heat in the ice and mantle. Beneath the frozen crust, water may circulate around rocky seafloors, where chemical gradients drive reactions akin to Earth's hydrothermal vents, enigmatic crucibles where life could emerge. Organic compounds, detected by spacecraft like Galileo, hint that the raw ingredients for biology are present, waiting in the dark for the spark of chemistry to ignite complexity. Farther from the sun, Saturn's moon Enceladus erupts with plumes of water and ice, venting directly into space. The Cassini spacecraft captured these towering geysers, revealing salts, organic molecules, and hints of molecular hydrogen, a potential energy source for microbial life. Each plume is a message from a hidden ocean, a cosmic Morse code suggesting that life could exist far from sunlight, where energy comes from pressure, chemistry, and tidal heating rather than photons. Here, the concept of habitability stretches beyond the familiar warmth of a star, suggesting that biology is more adaptable, more resilient than our terrestrial assumptions allow. Titan, Saturn's largest moon, presents yet another variation. Its surface is covered with rivers, lakes, and seas, not of water, but of methane and ethane, flowing beneath a thick, nitrogen-rich atmosphere. Beneath this hydrocarbon world, heat from the interior may maintain a liquid water ocean, possibly interacting with a rocky core to create conditions where prebiotic chemistry could flourish. In this alien crucible, life, if it exists, might follow pathways entirely unlike our own: silicon chemistry, exotic cell membranes, or metabolisms driven by chemical energy rather than sunlight. Titan demonstrates that the universe's laboratories for life need not shine. They only require energy, matter, and the patience of eons. On these icy worlds, life may operate in ways that challenge human imagination. Microbes could swarm around hydrothermal vents, forming the foundations of complex ecosystems independent of photosynthesis. Chemosynthetic processes, powered by gradients of hydrogen, sulfides, or ammonia, could support organisms that grow, reproduce, and evolve in complete darkness. Life may twist around energy sources that seem marginal by earthly standards, turning pressure, tidal heating, and chemical imbalance into the engines of survival. The emotional resonance of these moons lies in their quiet insistence. Life need not be obvious to exist. It does not have to shine to matter. The universe may teem with hidden biospheres, stretching the definition of life beyond the warmth of a habitable zone. Every plume of Enceladus geysers, every fracture in Europa's ice, and every hydrocarbon lake on Titan hints at ecosystems that evade detection, waiting for human curiosity to pierce the layers of ice and distance. Each discovery reframes the cosmic perspective. Perhaps the silence humanity interprets as absence is, in fact, life too subtle, too hidden, or too remote for our current instruments to perceive. Astrobiologists have begun to imagine missions designed specifically to explore these secret oceans. NASA's Europa Clipper, scheduled to arrive in the coming decade, will map the ice shell, sample plumes, and analyze chemical signatures, searching for the faintest evidence of habitability. Concepts for subsurface probes and ice-penetrating drills aim to pierce kilometers of frozen crust, reaching the waters where chemistry might have blossomed into biology. Enceladus remains a tantalizing target. Future orbiters could capture more detailed compositions of its plumes, seeking biosignatures that reveal metabolic processes. Titan, with its thick haze and frigid temperatures, demands new technologies, submersibles for hydrocarbon seas, drones for atmospheric exploration, expanding humanity's reach into alien biochemistry. The implications of subsurface life are profound. If organisms exist beneath the ice of Europa or Enceladus, intelligence may not need to wait for Earth-like conditions to emerge. Life may arise wherever chemistry permits, wherever energy flows, wherever matter organizes in patterns that resist entropy. The universe, once thought sterile beyond the habitable zones of stars, may harbor thriving oceans under layers of ice, worlds that do not shine yet sustain complexity. These hidden realms suggest that life is not rare, merely concealed, awaiting the patient gaze of instruments capable of reaching the dark. Philosophically, these icy oceans challenge the human-centric notion of significance. Life may flourish where it is invisible to us, indifferent to our gaze, existing quietly as it evolves, adapts, and perhaps even communicates in forms beyond detection. It suggests a cosmos that is not lonely, but discreetly alive, a tapestry of hidden ecosystems that defy expectation. Humanity's place in the universe is reframed. Intelligence, like life itself, may not be the sole arbiter of meaning, but a participant in a broader, subtler cosmic symphony. In the final measure, the ocean worlds teach a lesson in humility and wonder. They hint that the universe's vitality may be submerged, flowing silently beneath layers of ice and distance, where life is an undercurrent of complexity invisible to the casual observer. The search for extraterrestrial life must expand beyond the luminous and obvious, learning to listen to the subtle currents of chemistry, tides, and pressure that shape the hidden biospheres of other worlds. Europa, Enceladus, Titan, all remind us that life may be pervasive, yet hidden, a quiet testament that the universe does not need to shine to be alive. The story of life on these frozen moons invites reflection, that existence itself is more resilient than light alone can reveal, and that humanity, gazing outward, must prepare not for empty darkness, but for oceans of hidden possibility, awaiting discovery beneath ice that does not shine. Across the void, humanity has extended its senses, fashioning instruments that stretch imagination into the silent depths of space. These are not mere machines. They are the archaeologists of the cosmos, brushing away the dust of light years to uncover the traces of distant worlds and the faint echoes of civilizations we may never meet. Each telescope, each probe, each detector is a tool designed to sift the vast cosmic canvas for patterns that speak of life, of intelligence, of a universe more alive than our unaided eyes could ever perceive. The James Webb Space Telescope floats in the cold darkness beyond Earth's warmth, a golden eye turned outward. Its infrared vision pierces dust clouds and starlight, revealing exoplanets in glimmers and shadows. Webb's instruments perform spectral fingerprint scanning, analyzing the absorption and emission lines of distant atmospheres. Oxygen, methane, water vapor, carbon dioxide, all leave delicate signatures, whispering chemical stories that may indicate the stirrings of life. With each spectrum captured, humanity reads the language of chemistry written on alien skies, tracing the balance of elements that may nurture biology. On Earth, large radio arrays scan the heavens with patient persistence. The Very Large Array in New Mexico, the Square Kilometer Array under construction across hemispheres, and other radio observatories stretch their ears toward the cosmos. Each antenna is attuned to the faintest ripple of electromagnetic communication, listening for signals that could traverse decades, centuries, or millennia of space. AI-powered anomaly detection now aids these arrays, filtering cosmic noise to isolate patterns too subtle for human intuition alone. The hope is not just to detect life, but intelligence, deliberate attempts at communication from civilizations that may have risen and fallen long before our own. Closer to home, robotic explorers prepare to penetrate the frozen secrets of moons that do not shine. The Europa Clipper, set to arrive at Jupiter's icy moon in the coming decade, will map fractures in the ice, analyze plume compositions, and search for chemical gradients suggestive of habitability. Dragonfly, a rotorcraft destined for Titan, will traverse hydrocarbon dunes, sampling organic-rich regions, measuring atmospheric chemistry, and seeking prebiotic or even biotic signatures. These missions do not merely observe, they reach into alien worlds, extending humanity's senses into oceans and lakes hidden beneath ice or clouds, searching for life that exists beyond light and warmth. The search for technosignatures, the fingerprints of advanced civilizations, has also evolved. Megastructures, if constructed, would alter the light of their host stars, producing subtle dips or anomalies in brightness. Infrared heat mapping scans for waste energy from civilizations manipulating planetary, stellar, or even galactic-scale engineering. Lasers, hypothetical or natural, may broadcast across interstellar distances, and arrays now scan systematically for narrowband pulses, artificial in origin, designed to traverse the darkness of space. Each of these methods transforms the universe into a laboratory, testing hypotheses that once existed only in thought experiments or equations. Every instrument, every observation, is an act of cosmic archaeology. Exoplanet atmospheric models, informed by data from space telescopes and spectroscopy, attempt to reconstruct the environmental histories of distant worlds, tracing the chemical fingerprints left by volcanism, oceans, or biology. Radio telescopes trace the faint echoes of civilizations, listening for the deliberate or accidental signals that might reveal themselves across decades or millennia. Spacecraft journey into alien environments, sampling, mapping, and measuring in the service of discovery. Humanity's tools are extensions of curiosity, translating photons, radio waves, and chemical compositions into a story about life beyond Earth. These searches confront both technical limits and cosmic patience. Signals degrade over distance, light arriving centuries after leaving its source. Atmospheric compositions can be ambiguous, spectral lines overlapping with multiple possible explanations. Radio searches contend with background noise from the galaxy itself, human-generated interference, and the sparsity of deliberate transmissions. Even the most advanced instruments can only observe a fraction of the sky, a fraction of time, leaving the vast majority of the universe silent, unexamined. Yet each scan, each measurement, each calculated model adds a stroke to the vast, unfinished painting of our cosmic understanding. Artificial intelligence now assists these endeavors, revealing anomalies hidden in the vast datasets generated by telescopes and orbital sensors. Machine learning algorithms sift through terabytes of spectral data, searching for atmospheric combinations that hint at biology or signal patterns too complex to arise naturally. In the future, these systems may guide human decision-making, suggesting where to point telescopes, which stars to prioritize, and which planetary systems may hold the richest stories of life. AI becomes the quiet partner in exploration, translating the universe's subtle codes into hypotheses for human minds to contemplate. SETI, the search for extraterrestrial intelligence, has expanded its network, coordinating across continents to create a grid of listening stations capable of simultaneous, high-resolution surveys. The observatories work in concert, triangulating anomalies, cross-verifying signals, and attempting to distinguish natural cosmic phenomena from deliberate communication. Each detected pulse, each transient event, is scrutinized, recorded, and cataloged, a cosmic ledger of possibility. The silence of decades of listening is itself a message, one that must be interpreted alongside the data, the statistics, and the philosophical implications of waiting in a universe so vast and indifferent. Even planetary heat mapping and megastructure searches extend humanity's reach. Infrared surveys of galaxies seek signs of energy harnessed on unimaginable scales. Waste heat from civilizations manipulating stellar or planetary systems could betray their presence long after they have risen, or perhaps while they operate beyond our capacity to detect. These searches challenge conventional notions of visibility, reminding us that intelligent life may not illuminate the cosmos in ways we expect, but may instead move quietly, deliberately, efficiently, hidden in plain sight. The instruments humanity has built, collectively, form a narrative of patience and ingenuity. Each probe, telescope, and array is a manifestation of a species reaching beyond its home, translating curiosity into measurement, speculation into observation. They are the eyes, ears, and fingers of a civilization probing the cosmic dark, seeking answers to questions as old as consciousness itself. In their quiet operation, they bridge the gap between imagination and reality, between the abstract possibility of extraterrestrial life and the empirical pursuit of its evidence. Ultimately, these tools are a testament to human hope. They extend not only technical capacity but philosophical ambition. They ask whether the universe is fundamentally solitary or secretly teeming with life, whether intelligence is rare or inevitable. Each observation, each measurement, carries the weight of existential reflection, that by seeking outward, humanity seeks inward, probing the fundamental conditions of life, consciousness, and meaning. The James Webb Telescope captures starlight to read atmospheric stories. Radio arrays listen for whispers across millennia. Europa Clipper and Dragonfly venture into frozen oceans and hydrocarbon seas. Collectively, they act as cosmic archaeologists, uncovering layers of reality, possibility, and wonder buried across the silent expanses of space. In this era of exploration, humanity's gaze is no longer limited by the naked eye. Spectra, radio waves, and orbital measurements become the vocabulary of discovery. Each dataset, each mission, each scanning program is a stanza in a poetic dialogue with the universe. The cosmos responds not always with clarity, but with hints, with chemical traces, with subtle patterns in light and shadow. Humanity listens, interprets, and imagines, knowing that the universe may be alive with phenomena beyond direct observation, that intelligence may hide in forms invisible, and that the act of searching is itself a profound reflection on existence. Even as the silence persists, these tools remind us that the search is not passive. It is an active, methodical, patient engagement with the cosmos. Instruments like the James Webb Space Telescope, large radio arrays, planetary missions, AI detection systems, and technosignature surveys transform vast emptiness into a terrain of inquiry, each measurement a probe into the profound question: are we alone, or are we late observers of life already thriving beyond our reach? In the end, humanity's instruments are more than hardware. They are extensions of our curiosity, empathy, and courage. They map not only stars and planets but the contours of possibility itself, tracing a path through the darkness toward understanding, toward discovery, toward the subtle, often hidden manifestations of life and intelligence that may exist in the universe's quiet, unlit corners. And as these tools continue to search, they remind us that our place in the cosmos is both humble and immense, a participant in a vast, patient, and ongoing investigation of the very nature of life, time, and consciousness itself. The universe speaks in light, in the spectral fingerprint of each atom, molecule, and particle, and humanity has learned to listen. Every photon captured from a distant world is a messenger from across space and time, carrying the secrets of chemistry, climate, and perhaps even life itself. In recent years, these whispers have begun to hint at something extraordinary: a subtle discord in planetary atmospheres, a chemical imbalance that does not quite fit the natural patterns astronomers expect. Oxygen paired with methane, molecules that should react and vanish within centuries, persist together on exoplanets many light-years away. The effect is faint, almost imperceptible, like a distant note out of key in a vast cosmic symphony, but it is enough to stir wonder and caution in equal measure. These discoveries, catalogued through the combined power of the James Webb Space Telescope and ground-based spectrographs, suggest worlds in chemical disequilibrium. In principle, such imbalances could arise from natural processes, volcanism, photochemistry, or deep ocean atmosphere exchanges, but the more detailed the measurements, the less natural the explanation sometimes seems. Certain oxygen-methane ratios mimic the industrial fingerprints of a civilization. Molecules like nitrogen oxides, chlorofluorocarbons, or exotic halocarbons, products that on Earth are predominantly human-made. If these chemical signals are real, they could be the first signs of intelligent life altering its planet on a global scale. Astronomers have also detected unusual heat signatures, planets radiating more infrared than expected, their thermal profiles inconsistent with simple solar heating. Some show localized anomalies, concentrated in regions that could, in principle, correspond to megastructures or industrial hubs. Spectral scans of these worlds occasionally reveal unexplained variations. fluctuations in molecular concentrations, transient spikes of chemical activity, or atmospheric constituents appearing without known natural precursors. The data are tantalizing, but the universe is a cunning mimic. Cosmic dust, photochemical quirks, and measurement noise can imitate the patterns of deliberate engineering, and caution tempers the excitement. The discovery of these chemical noises has prompted intense debate within the scientific community. Each candidate detection undergoes rigorous cross-validation, repeated observations, and modeling to rule out terrestrial interference or instrumental error. Observatories coordinate worldwide, combining datasets from multiple wavelengths, infrared, visible, ultraviolet, to confirm whether an anomaly is real. A single anomalous spectrum can be a statistical fluke. Multiple correlated anomalies might suggest something more profound. At the same time, computational simulations allow scientists to reconstruct planetary atmospheres over millennia, testing whether observed compositions could arise through natural processes alone. In nearly every case, nature offers a plausible explanation, but the possibility of artificial influence lingers, a shadow in the data, neither confirmed nor dismissed. Consider the extraordinary implications if even one of these signals were genuine. Life capable of modifying a planet's chemistry represents not just biology but intelligence, technology, and civilization. Detecting it would mean peering across interstellar gulfs and glimpsing the handiwork of a species that has transformed its environment on scales we can only speculate about. Yet we remain blind to direct evidence. The chemical hints arrive long after the photons leave their source, delayed by decades, centuries, or millennia. What we see today may reflect civilizations long vanished, or perhaps just beginning. The signals, if real, are echoes of a cosmic history we cannot yet read. The human mind, trained for patterns, struggles with such ambiguity. Each unusual spectrum is a riddle. Is it the product of complex natural chemistry or a signature of intelligence reaching across the void? The tension is both exhilarating and humbling. Unlike radio signals or visible megastructures, these chemical hints are ephemeral, fragile, and open to interpretation. A single measurement can spark headlines, ignite debate, and challenge assumptions about life's rarity, but no discovery has yet been definitive. The universe seems to taunt us, offering tantalizing glimpses, yet withholding certainty. These chemical whispers exemplify a fundamental truth. Science progresses through patience and skepticism. Researchers understand the stakes. False positives could mislead generations, while missed opportunities might leave civilization unaware of profound reality. Thus, teams develop protocols for verifying anomalies, employing multiple telescopes, independent data reduction pipelines, and repeated temporal observations. Each detection is tested against the full range of known astrophysical processes: photodissociation, planetary volcanism, ocean chemistry, solar activity, cosmic ray interactions. Only when all natural explanations falter does a hint gain the tentative label of potential technosignature. Even then, it remains a hypothesis, a suggestion of possibility rather than proof. At the same time, the very act of searching has transformed planetary science. Spectroscopy, once a tool for mapping stellar and planetary compositions, now becomes a means of indirect archaeology. Every measured atmosphere, every chemical ratio, is a record of energy flows, geological cycles, and perhaps intelligence. We have begun to see planets not as static spheres of rock and gas, but as dynamic laboratories, each with its own history, chemistry, and potential for life. In this context, chemical disequilibrium is a message waiting to be deciphered, a conversation across light years that requires patience, rigor, and imagination. Yet the emotional weight is profound. Humanity stands closer than ever to detecting life beyond Earth, yet remains blind. Each tantalizing anomaly carries hope and frustration in equal measure. We measure, model, and monitor, knowing that the universe may offer no confirmation for decades. The silence surrounding these potential signals mirrors the broader Fermi paradox. The cosmos is vast, ancient, and overwhelmingly indifferent. And yet, within that silence, faint signals, chemical imbalances, thermal anomalies, spectral deviations, persist, whispering the possibility that we are not alone. Ultimately, these new shocks of chemical noise are both a promise and a caution. They remind us that life may be more common than previously imagined, but intelligence, civilization, and detectable technosignatures may remain rare, transient, or difficult to perceive. Science stands on the edge of discovery, peering into the spectral depths of distant worlds, translating photons into meaning and grappling with the unknown. The chemical hints are fragile, almost ephemeral, yet they embody the culmination of centuries of inquiry, technology, and imagination. In the end, humanity's gaze is precise, patient, and methodical, yet it confronts the limits of perception imposed by distance, time, and the subtlety of cosmic processes. The chemical anomalies that provoke excitement today may one day form the first confirmed signatures of extraterrestrial civilization, or they may vanish under closer scrutiny, leaving only questions. And still, the search continues, instruments pointed outward, minds attuned to patterns, hearts open to the possibility that somewhere, across the void, life not unlike our own, intelligent, complex, and far-reaching, might be quietly writing its own spectral stories into the cosmos, waiting for another species to listen. Humanity stands poised between knowledge and mystery. The chemical hints are a shock not because they prove life, but because they suggest it might be closer than ever imagined, yet perpetually beyond certainty. Science listens with all its instruments, from the James Webb Space Telescope to Earth-based spectrographs, from orbital probes to AI analysis pipelines. Each measurement is a step into the darkness, each spectrum a potential message. And even if confirmation never comes, the pursuit itself, patient, meticulous, and profound, is a testament to the enduring human desire to understand our place in a universe that may be whispering secrets just out of reach. Here, in the faint chemical discord of distant worlds, science stands at the edge, closer than ever, yet still blind, poised between the thrill of potential discovery and the humbling silence of the cosmos. Imagine a moment when the universe no longer feels silent, when the isolation of countless millennia dissolves into revelation. Humanity has gazed at the stars for tens of thousands of years, crafting myths, philosophies, and religions to fill the void between the observer and the observed. Yet even in our science, even in our meticulously gathered data, the cosmos has seemed indifferent, vast, and unmoving. But what if that perception were shattered? What if the first unambiguous evidence of extraterrestrial intelligence arrived? A signal, a technosignature, a subtle pattern in the chemical heartbeat of a distant world that says, unmistakably, we are not alone. Such a discovery would ripple across every layer of human understanding. Religions, long grounded in the uniqueness of Earth, would face profound reinterpretation. Sacred narratives, once Earth-centered, would expand to accommodate life elsewhere, perhaps reimagining creation as a cosmic process rather than a terrestrial event. Philosophy, too, would shift. Epistemology and ethics, long calibrated to human experience, would confront the challenge of beings with intelligence and culture wholly foreign, yet undeniably present. Questions about morality, existence, and consciousness would take on a new urgency, for we would be compelled to consider our place within a community far greater than our solar system. The emotional landscape of humanity would transform. The cosmic loneliness that has shaped our species' self-perception, the notion that the universe is a silent expanse in which humanity floats, fragile and solitary, would begin to fade. For the first time, there would be a tangible sense of connection, a reassurance that intelligence, consciousness, and creativity are not unique to this small blue planet. The discovery would not merely be scientific, it would be existential. We would understand that life, in some form, can flourish elsewhere, and that intelligence may be a thread woven into the universe's fabric, not a solitary anomaly. Communication would enter an entirely new domain. Even if the first contact is indirect, a pattern in light or an encoded signal, the knowledge of intelligent others would compel the creation of a universal language, a bridge spanning unimaginable distances and epochs. The physics of transmission, the mathematics of signal encoding, the philosophy of intention, all would become tools of interstellar diplomacy. Humanity would no longer only interpret the universe, we would begin to negotiate our place within it. Science itself would evolve. The detection of extraterrestrial intelligence would confirm hypotheses that have long hovered at the edge of speculation. Fields like astrobiology, exoplanetary science, and quantum communication would find new focus and urgency. Every planetary atmosphere, every spectral anomaly, would be scrutinized not only for signs of chemical imbalance but for evidence of purposeful design. Technologies now theoretical, artificial intelligence capable of decoding alien signals, quantum networks capable of transmitting information across light years, would become necessities, reshaping civilization's technological landscape. Perhaps most profoundly, the discovery would redefine humanity's identity. Earth would no longer exist in cosmic solitude. It would be a member of a larger community, a single voice in a chorus of intelligent life. National boundaries, cultural divisions, even the categories that define human society would appear diminutive in comparison to this new perspective. The knowledge that other civilizations exist, other minds, other histories, other ways of experiencing reality, would foster a sense of cosmic citizenship. Humanity would become a participant in a narrative far greater than its own, a story of intelligence and consciousness playing out across the galaxy. Yet the psychological effects would be complex. Wonder would be intertwined with humility, curiosity with caution. The realization that civilizations can rise, communicate, and perhaps even vanish would instill a reverence for both the fragility and the resilience of life. We would confront the possibility that some civilizations are unimaginably advanced, operating beyond our comprehension, leaving signals so subtle they could be mistaken for background noise. The awareness of our own limitations, juxtaposed with the knowledge of others' existence, would redefine ambition, creativity, and aspiration. Even geopolitics and culture might be transformed. Humanity's collective attention, previously fragmented across conflicts and competitions, could redirect toward common goals: interstellar observation, preservation of knowledge, and preparation for eventual interaction. Education would emphasize cosmology, astrophysics, and communication theory, alongside philosophy and ethics designed for a post-contact era. The arts would reflect a universe alive with intelligent life, creating narratives and expressions that explore both wonder and caution. The discovery of extraterrestrial intelligence would seed not only science but imagination, giving rise to a cultural renaissance on an interstellar scale. Science fiction, once speculative, would become anticipatory. The concepts that shaped human dreams, the ethics of first contact, the dilemmas of interstellar diplomacy, the architecture of civilizations managing solar systems, would transition from imagination to plausible reality. We would reinterpret literature, art, and history in the context of a universe alive with intelligence, finding echoes of extraterrestrial possibility in human creativity. Dreams of the stars would gain tangible context, and the barrier between speculation and reality would blur. Yet even as the euphoria of discovery spreads, caution would remain necessary. Understanding another civilization requires humility and patience. Signals might be misinterpreted, behaviors misunderstood, intentions unknown. The ethical implications of responding, or even broadcasting our own presence, would demand rigorous contemplation. Humanity would need to develop frameworks not only for observation but for engagement, balancing curiosity with prudence, desire for connection with awareness of potential hazards. On a cosmic scale, the discovery of life elsewhere would offer perspective on our own civilization's trajectory. The great filter, the fragility of intelligence, and the challenges of sustaining technology across millennia would become more than abstract concepts. They would transform into urgent, tangible considerations. Civilizations elsewhere may have faced crises we have yet to encounter, and their absence or survival would guide our understanding of existential risks. Every anomaly, every exoplanet, every atmospheric fluctuation would carry new weight, as potential lessons in the delicate art of maintaining intelligent life. Ultimately, finding them would mark a transition from isolation to participation. Humanity's narrative, long confined to a single planet, would expand into the galactic story. The stars would no longer be distant points of light but potential centers of intelligence, each with a history, a culture, and perhaps a message. Cosmic citizenship would replace planetary solitude, imbuing every human endeavor with the knowledge that our species is part of something far greater. The universe, once silent, would have become a forum, a place of observation, speculation, and dialogue, and humanity would be ready to listen, to respond, and to exist as an active participant in the broader story of intelligent life. The profound shift would not be merely external, it would be internal. Our perception of self, of purpose, and of destiny would be forever altered. The recognition of other intelligences would dissolve the sense of cosmic exceptionalism, replacing it with humility and awe. The human species, once defined by survival on a single world, would redefine itself as a member of a galactic continuum, a participant in a network of intelligence that stretches across space and time. Knowledge of their existence would provide not just answers but orientation, a new framework for meaning in a universe where consciousness is no longer solitary, where awareness is a shared phenomenon, and where every thought, invention, and question is potentially echoed across light years. In this new era, Earth becomes simultaneously familiar and profoundly new. It is home, yet no longer alone. Humanity is ourselves, yet also part of a community that extends beyond comprehension. The discovery of intelligent life elsewhere would not simply be a scientific milestone. It would be a philosophical awakening, a cultural transformation, and an emotional revelation. Isolation would give way to connection, silence to conversation, and the cosmos would finally feel populated not only by stars and planets but by minds, histories, and possibilities. And in that moment, the question that has haunted humanity for centuries, are we alone? Would find its answer, and with it, everything changes. If we never find them, what are we? In the vast darkness of the cosmos, silence can be deafening. Across billions of stars, each a sun to worlds unknown, the light travels, carrying with it the echoes of possibility, and yet no answer arrives. No signal interrupts the emptiness. No whisper of civilization breaks the indifferent hum of space. The universe may be waiting and we may be the first. Or perhaps we are alone, not in the sense of loneliness, but as the singular spark of awareness, the first intelligence awake, shining a conscious light into a dark, uncaring expanse. To consider this possibility is to confront both wonder and responsibility. If humanity is the first intelligence, then existence itself becomes an extraordinary miracle, a solitary occurrence in a universe otherwise untouched by thought. Every choice, every invention, every act of preservation gains weight beyond comprehension. The stars are no longer just distant objects of curiosity, they are witnesses to our awakening. The vacuum is no longer empty, it is an arena demanding stewardship. Life's fragile emergence on Earth, shaped over billions of years of planetary chance, becomes a gift of incalculable magnitude and a duty. Duty to continue, to explore, to ensure that consciousness does not fade into the void. If no other voice arises, humanity must become the universe's witness, its chronicler, its storyteller. Every discovery, every insight, every message we craft carries forward the knowledge of a single intelligent species, potentially for millennia to come. We are charged with the expansion of awareness, entrusted with transforming mere existence into understanding, and understanding into action. The search for others becomes a mirror for the search for ourselves, as we learn to act as both origin and echo. If we are alone, the task is profound. Knowledge becomes sacred, memory becomes eternal, and the dissemination of consciousness a moral imperative. Our technologies, the telescopes that scan the heavens, the robotic emissaries that wander icy moons, the quantum networks that whisper across light years, become instruments not only of observation but of preservation. They are lighthouses, casting signals outward into the void, carrying the essence of thought, intention, and curiosity. Humanity becomes a vessel of continuity, a steward of intelligence in a universe that may never again host another mind. Yet this solitude carries paradoxical beauty. To be the first is to define the trajectory of all intelligence that may one day follow. Our culture, our ethics, our science, all become templates, experiments of possibility. Civilization is no longer a local endeavor but a cosmic statement, proof that intelligence can emerge, survive, and act. The contingency of life on Earth, its precise chemistry, its planetary stability, its long evolutionary march, gains philosophical significance. We are both a miracle of probability and a potential seed for something greater, the first chapter in a story that may stretch across the galaxy. Every human endeavor, from the simplest act of creation to the most complex scientific experiment, assumes cosmic relevance. To write a book, to compose music, to record knowledge, to send probes outward, all are acts of eternal significance, if no other civilization exists to bear witness. Humanity becomes the universe's voice, the consciousness that converts unfeeling matter into aware observation. We are not just observers. We are participants, responsible for ensuring that life's spark does not remain confined to a single pale blue, flickering and fragile against the cosmic night. The responsibility extends to the future. If humanity is alone, then we must protect life, preserve knowledge, and expand consciousness wherever possible. We must learn to steward planets, to stabilize civilizations, to guide evolution of intelligence without repeating the errors that have silenced potential elsewhere. Survival becomes not merely a biological imperative but a philosophical one. Existence itself becomes sacred, and the act of sustaining awareness a moral duty writ across time. Our collective attention, once limited to survival and culture on Earth, must turn outward and forward simultaneously toward preservation across light years and millennia. In this scenario, silence is not despair but a call to action. The absence of other voices imposes urgency. The universe may not correct our failures, and there is no external safety net. Consciousness is both fragile and precious. Knowledge is not optional. It is the inheritance we leave for the future. Civilization's longevity becomes a measure of responsibility, a reflection of the universe's faith in its first observers. Every technological advancement, every step into space, every attempt to archive or transmit understanding is a vote against eternal night, a declaration that life, thought, and curiosity will persist even if they have no companions. Even as we consider the possibility of cosmic solitude, there is space for wonder. We are alive in a universe capable of generating intelligence, and that fact alone is profound. Life is the defiance of entropy, the emergence of order from chaos, the creation of awareness from inert matter. To be first is to be witness to this fundamental miracle, and to act with the awareness that such a miracle may be unique. Humanity must embrace both humility and courage, recognizing the limits of comprehension while asserting the potential for creativity, stewardship, and expansion. Philosophically, the question transforms from, "Are we alone?" to, "What are we called to become?" If no other voice arises, the cosmos asks us to step forward as origin and echo simultaneously. We must cultivate knowledge, preserve awareness, and transmit our understanding, not merely for ourselves, but for the universe itself. Silence becomes a responsibility, and isolation becomes purpose. The absence of others magnifies the value of every human thought, every act of preservation, every reach into space. Humanity is both the question and the answer, the mirror and the light. And yet, even in solitude, uncertainty remains. Life may exist elsewhere, waiting in forms too subtle for detection, or intelligence may be emerging on planets we have yet to observe. The universe's verdict is not yet written, and the possibility that we are alone must coexist with the hope that we are part of a larger network, unseen but extant. Humanity must act as if it is alone, while remaining open to discovery. Our responsibility is eternal, but our hope must remain expansive. In the end, searching for others is inseparable from searching for ourselves. Each telescope scan, each exoplanet catalogued, each signal analyzed, is not merely a quest for companionship but a reflection of our own consciousness reaching outward. We are either the echo or the origin. We are either part of an ongoing chorus of intelligence, or we are the first note struck in a universe that has never heard awareness before. And in either case, the weight of possibility falls upon us. The universe waits, patient, vast, indifferent in its immensity. Yet within this waiting, there is opportunity. The question of whether life is everywhere, or whether humanity is the solitary spark, is not a question for which immediate answers can arrive. It is a question for which action, preservation, and the conscious exercise of responsibility are themselves the response. Humanity may never receive an answer, yet every effort to extend knowledge, to preserve consciousness, to reach into the stars, becomes an answer in practice. Life either is everywhere, waiting for discovery, or we are the first spark in eternal night. The search for others becomes the search for meaning, the attempt to render a silent universe aware. If no other intelligence arises, humanity must carry the torch, transform existence into awareness, and ensure that the universe itself is not left unobserved. The act of observing, of knowing, of preserving consciousness, is a moral and philosophical imperative, and through it, the universe gains its voice, however delayed or solitary it may be. And so we are left with possibility. No certainties. No closure. Only the invitation to act, to preserve, to create meaning in the face of cosmic silence. Humanity is the witness, the steward, and perhaps the first voice. And the cosmos waits, patient and eternal, for whichever truth we prove, whether we are alone, or whether we are only the beginning of an immense, yet unseen chorus of life. The universe waits. And we are the ones who may answer.